Audio review of textbook for Class 12. Physics Part 2.
All right, ever catch yourself just looking around and thinking, wow, how does seeing even work? It's one of those things, you don't think about it until you really think about it.
Yeah, it's pretty wild.
Today, we're tackling Chapter 9, Ray Optics and Optical Instruments.
Perfect. And you've got, looks like a good old physics textbook here, all about how light behaves and all the really cool stuff we can build when we understand light.
Exactly. Consider this your crash course in the science of light. We're going to start with the fundamentals. Reflection, refraction, and then we'll see how those simple ideas let us create things like, microscopes to see the tiny world, or telescopes to look at galaxies far, far away. Our vision, if you choose to accept it, is to break down the key ideas, maybe uncover some surprises along the way, and hopefully have some fun while we're at it. You ready for this?
I'm ready. Let's shed some light on this.
Nice. So, Chapter 9 kicks off with, well, what is light? I mean, we all experience it every day, but we don't always think about what's actually going on.
Right, we know it travels crazy fast, and, in straight lines, most of the time.
Like blink of an eye fast, right? The book even gives the official speed, the speed of light in a vacuum. It's like 2.99792458 meters per second.
Yeah, that's a mouthful.
Which, we can basically round to 10 meters per second. I mean, that's the universe's ultimate speed limit as far as we know, right?
That's as far as we know, yeah.
Yeah.
Nothing faster than that. But here's the thing. Earlier in the book, Chapter 8, it talked about light as an electromagnetic wave.
Okay, so now we're getting into the trippy stuff.
A little bit, yeah. Because, waves spread out. They don't travel in, perfect straight beams all the time.
Right. It's like saying sometimes a river acts like a solid metal rod. Doesn't quite compute.
Exactly. So how do we make sense of that? How can light be both a wave and, travel in these straight lines? Well, the answer is all about scale. See, the wavelength of visible light, the light we see, it's unbelievably tiny. We're talking nanometers here. Now compare that to the size of, your phone, a book, even a speck of dust. These things are billions of times bigger than the wavelength of light. So when light interacts with these huge objects compared to its wavelength, it kind of starts acting less like a wave and more like it's traveling in those straight lines. We call those straight lines rays. Think of it like if you're looking at waves on the ocean from far away, they look like they're moving straight towards the shore. But if you're right up close, you see all the ups and downs. A beam of light, it's just a bunch of these rays bundled together. So for understanding how light interacts with mirrors and lenses, on a scale that we can see and build stuff with, this ray idea, it's a really useful simplification.
So for our deep dive today, we're picturing light as these little straight arrows zipping around at the speed limit of the universe.
Got it. Now, what happens when these rays hit a surface? Like when you look in a mirror. We all know about reflections, but there's some serious science behind how it all works.
Right. Oh, absolutely. And the chapter breaks down the fundamental laws of reflection. The first one, it's all about angles. The angle at which the light hits the surface, that's called the angle of incidence, it's always exactly equal to the angle at which it bounces off the angle of reflection. Think of it like bouncing a ball perfectly off a wall. It goes in at one angle, comes out at the same angle. The second law tells us that the incoming ray, the outgoing ray, and the line that's perpendicular to the surface right where the light hits, that's called the normal, they all lie in the same flat plane. Everything stays nicely lined up in 2 dimensions. Kind of like a game of air hockey, right? The puck always stays on the table. Now, the book then dives into spherical mirrors. That's those curved mirrors like you see on the back of a spoon. Concave on the inside, convex on the outside. What makes those special when it comes to reflecting light?
It's all about that curve. With a spherical mirror, the normal line, that perpendicular line at any point, it always passes through the center of the sphere that the mirror is a part of. And that changes how parallel rays of light behave when they hit the mirror. Unlike a flat mirror that just sends those rays back parallel, a curved mirror can make them converge or spread out.
And there are a few key terms to keep in mind here. We've got the pole, which is the center of the mirror's surface, and the principal axis, which is the line that goes straight through the pole and the center of curvature.
Exactly. Imagine it like the mirror's center line. Now, to keep track of all these distances and directions, and to make sure our calculations don't go haywire, physicists use something called the Cartesian sign convention. It sounds fancy, but it's really just a set of rules about when to use positive and negative signs.
Okay, can you give us the quick rundown of the sign convention? I'm all about keeping things straight.
Sure. So first off, all distances are measured from the pole of the mirror. That's our starting point, or 0. Then we always consider the direction the incoming light is traveling as the positive direction. So, for example, if you've got an object in front of a concave mirror, the light's going from the object towards the mirror. To measure the object distance from the pole to the object, you're going in the opposite direction of the incoming light. So the object distance, which we call u, is usually negative. And then, for the image distance, which we call u, it depends on whether the image is real or virtual. If it's real, meaning the light rays actually converge to form the image, then v is positive. But if it's a virtual image, where the rays just appear to be coming from a point behind the mirror, then v is negative. And finally, for heights above the principal axis, those are positive, and below, negative.
Okay, so it's all about picking a reference point and sticking with it. And these same rules work for any kind of spherical mirror, which is handy. All right, next up is focal length. This sounds like it's the mirror's superpower, right? It's the ability to focus light.
You got it. So imagine you're shining a beam of parallel light rays towards a concave mirror. Now, if these rays are close to the principal axis, we call them paraxial rays, and they behave in a special way. After they bounce off the mirror, they all converge at a single point on that principal axis. That point is the principal focus, often labeled as F. And the distance from the pole to the principal focus, that's the focal length, which we call F. It's like the mirror's sweet spot for converging light. And the focal plane is just an imaginary plane that cuts through that focal point and is perpendicular to the principal axis. Any parallel rays, even if they're not parallel to the principal axis, will be focused somewhere on that plane.
Got it. So concave mirrors bring light together. Now, what about convex mirrors? Those curve outward, right? Do they have focal point too?
They do, but it's a little different. With a convex mirror, those parallel rays, they don't really converge. Instead, they spread out, they diverge. But if you trace those reflected rays backward, they all seem to be coming from a single point behind the mirror. That's the principal focus for a convex mirror. And the distance from the pole to that imaginary focus, that's its focal length. Figure 9.3 in the book is a good visual of this.
So concave mirrors converge light, convex mirrors make it spread out. Okay, now, the book mentions this neat relationship between the focal length f and the radius of curvature of the mirror r. They say f is always half of r. Why is that?
It's all about the geometry, really. Imagine a single ray coming in parallel to the principal axis and hitting the concave mirror at some point. Now, the normal at that point, it goes through the center of curvature. Because of the law of reflection, the reflected ray makes the same angle with the normal as the incoming ray did. Now, for those paraxial rays, the ones close to the axis, we can use some handy approximations, like the tangent of a small angle is basically equal to the angle itself. When you use these approximations and do a bit of triangle math, you find that the distance from the mirror to the focal point is exactly half the distance from the mirror to the center of curvature. So boom, F equals R2. It's neat how that simple relationship pops right out of the geometry.
Math and mirrors, a match made in physics heaven. Okay, so the focal length is half the radius of the curve. Now let's talk about the images these mirrors create. What's the difference between a real image and a virtual one?
A real image is one where the light rays actually meet at a point after reflecting off the mirror. If you put a screen at that point, you'd actually see the image projected onto it.
Okay, a projector, basically.
Exactly.
What?
Now, a virtual image is different. The rays don't actually meet. They just look like they're coming from a point behind the mirror when you see them.
Yeah.
Like when you look in a flat mirror, your reflection looks like it's behind the glass, but you can't actually touch it. That's a virtual image.
Right, it's all an illusion. And the book talks about these special go-to rays that help you figure out where an image will be. What are those all about?
These rays are super helpful when you're sketching out how a mirror will form an image. There are 4 main ones to remember, and figure 9.5 shows them really well. The first ray, it comes in parallel to the principal axis, and it bounces off so it goes right through the focus for a concave mirror, or it looks like it's coming from the focus for a convex mirror. The second ray, it goes straight through the center of curvature. That means it hits the mirror at a right angle and bounces right back along the same path. Third, you've got a ray that goes through or towards the focus and then reflects parallel to the principal axis. And lastly, there's a ray that hits right at the pole of the mirror. That one just follows the law of reflection, equal angles in and out. So if you draw any 2 of these special rays and see where they intersect or where they look like they intersect, bam, that's where your image will be. It's like a shortcut for figuring out the mirror's magic.
Nice. Cheat codes for optics. Now, all these distances, object distance u, image distance v, and focal length f, they're all connected by that super important equation, right? The famous mirror equation.
That's the one. The mirror equation is 1v plus 1u equals 1f. It's a beautiful thing. It ties together all the key players in image formation by a spherical mirror. And the book shows how it comes about using those similar triangles from ray tracing and by being careful with the sign convention. Like in the diagram, B prime P is negative V, FP is negative F, and BP is negative U because of the convention rules.
Right, got to watch those pluses and minuses. Now, along with the mirror equation, there's also magnification M. That tells us how much bigger or smaller the image is compared to the original object.
Absolutely. Magnification is just the ratio of the image height to the object height. And you can also get it by dividing negative V by U. Again, sign convention matters here. If is negative, your image is upside down, inverted. If it's positive, it's right side up, erect. And the magnitude of the number itself tells you how much bigger or smaller the image is. If it's greater than 1, it's magnified. If it's less than 1, it's diminished. And if it's exactly 1, well, the image is the same size as the object.
Okay, so we've got our two main tools for understanding spherical mirrors, the mirror equation and the magnification formula. And the book emphasizes that if we're careful with our signs, these equations work for all types of spherical mirrors, concave or convex, and for both real and virtual images. It's a pretty powerful toolkit. Now, let's look at some real-world examples to see how this plays out. The book asks, what happens if you cover up part of a concave mirror, like you slap a piece of tape over the bottom half? What happens to the image?
It's a great question. And it's one of those things where your intuition might lead you astray. You might think, well, if you block half the mirror, you'll only see half the image. But that's not how it works. Remember, light from every point on the object reflects off all parts of the mirror. So even with half the mirror covered, light rays from the whole object are still hitting the uncovered part and contributing to the image. What does change is the amount of light that's forming the image. So the image will get dimmer. In this case, about half as bright. Think of it like closing one eye. You still see the whole world, it's just a bit darker.
That's a really cool way to think about it. Okay, another example. What happens if you put a cell phone along the principal axis of a concave mirror? The book mentions that the magnification won't be uniform across the phone's image. Why would it be wonky?
Because different parts of the phone are at different distances from the mirror.
Yeah.
And remember, magnification depends on the object distance. So if the top of the phone is farther away from the mirror than the bottom, it'll have a slightly different magnification. That leads to a distorted image. It won't be a perfectly scaled up version of the phone.
Okay, so different distances, different magnifications, different image sizes. It's like a funhouse mirror effect. And the book also goes through some specific numerical examples, right? Let's try one. What if we have a concave mirror with a radius of curvature of 15 centimeters? That means its focal length is half that, so 7.5 centimeters. Now let's put an object 10 centimeters away from it.
Okay, we can totally work that out. Remember, for a concave mirror, the focal length is negative, so f equals negative 7.5 centimeters. The object is in front of the mirror, so the object distance u is also negative. U equals angus 10 centimeters. Now let's plug those values into the mirror equation. 1v plus 1u equals 1f. Solving for v, the image distance, we get v equals negative 30 centimeters, and the magnification, m equals medical v, which turns out to be made of a 3.
So what does all that tell us about the image?
Well, the negative v means the image is 30 centimeters in front of the mirror. That means it's a real image formed by the actual convergence of light rays. The magnification of x out of a 3 tells us two things. The negative sign means the image is inverted, upside down. And the magnitude of 3 means it's 3 times bigger than the object.
Okay, so we have a real inverted and magnified image. Cool. What if we move the object even closer to the mirror, let's say just 5 centimeters away?
Let's see what happens. Now, u is negative 5 centimeters. We still have the same focal length, f equals 7.5 centimeters. Plugging those into the mirror equation, we get a value of positive 15 centimeters. And the magnification is now positive 3.
Positive v, that's different. What does that mean?
A positive v for a concave mirror means the image is behind the mirror. It's a virtual image, not formed by actual converging rays. And the positive magnification means it's erect, right side up, and magnified by a factor of 3. So just by moving the object closer than the focal point, the image flips from real and inverted to virtual and erect.
Right, it's like crossing a magic boundary at the focal point. The book also has an example with a convex mirror, the kind you often see in car side mirrors. It mentions a jogger running toward a convex mirror and asks how fast their image seems to be moving. This feels like one of those things that tricks your brain when you're driving, right?
It definitely is. Convex mirrors, remember, they always produce virtual, erect, and diminished images. Things always look smaller. What's interesting here is that even if the jogger is running at a constant speed, the speed at which their image appears to be moving in the mirror, it's not constant. The book even does the calculations. As the jogger gets closer and closer to the mirror, their image seems to speed up. That's why those warnings on car mirrors say objects in mirror are closer than they appear, because they're not just smaller. They seem to be approaching faster than you'd expect based on their actual speed.
Yeah.
It's all because of how the image distance changes in the mirror equation as the object gets closer.
Right, you get that feeling like the car behind you is suddenly right on your tail, even though it's pretty far back a second ago. It's physics messing with your perception. Okay, we've been reflecting on mirrors. Let's switch gears now and talk about what happens when light passes through something, like when it goes from air to water or from air to glass. That's refraction, right? The light bends.
Exactly. When light travels from one transparent material to another at an angle, its speed changes. And that change in speed is what causes the bending, the refraction. It's like when you're running on the beach and one leg hits the soft sand first. You kind of veer off course.
That's a great analogy. So what are the rules that govern this bending of light?
There are two main laws of refraction, often called Snell's laws. The first one is about the plane of action, just like with reflection. The incoming ray, the refracted ray, the one that goes into the new material, and the point of incidence, they all lie in the same plane, both 3D shenanigans. The second law is the quantitative one. It says that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant. That constant is called the refractive index, and it's usually represented by the letter n. So sin I divided by sin r equals n. And this n, this refractive index, it depends on the two materials involved. Like air and water have a different refractive index than air and glass. It also depends a tiny bit on the color of the light.
Okay, so n is like a measure of how much a material bends light. And if n is greater than 1, that means the light slows down in the second material, right? Like glass is optically denser than air.
You got it. And because the light is slowing down, it bends towards the normal. If n is less than 1, the light speeds up and it bends away from the normal.
Gotcha. Makes sense. Now here's a thought. Is optical density the same as just regular density, like how heavy something is?
That's a tricky one. They're not always the same. You can have a material that's lighter than another, but light travels slower in it. Like the book mentions turpentine and water. Turpentine is less dense than water, but it has a higher refractive index, so light actually travels slower in turpentine even though it's lighter. Don't let that trip you up.
Wow, counterintuitive. So heavier doesn't always mean slower for light. And the book mentions some relationships between refractive indices, right? Like if you know how much one material bends light compared to another, you can figure out other combinations.
Exactly. Let's say you know the refractive index of material 2 with respect to material 1. We call that on sub 21 double. Well, the refractive index of material 1 with respect to material 2 and sub 12 is just the reciprocal, 1 over in sub 21 foots. And if you have 3 materials and you know the refractive indices of 2 pairs, you can multiply them to get the refractive index of the third pair. It's all about how much the light bends relative to each material.
Okay, that's a handy shortcut for optics problems. Now, we see refraction happening all around us. The book talks about shining light through a rectangular glass slab. What happens there?
So imagine a ray of light hitting a glass slab at an angle. It first goes from air to glass, so it bends towards the normal because glass is denser. Then when it exits the slab, it goes from glass to air, so it bends away from the normal. The cool thing is, because the two surfaces of the slab are parallel, the light ray ends up traveling in the same direction it started in. It's just shifted a bit sideways. We call that lateral shift.
So it's like it took a little detour through the glass, and then there's that classic effect where a straw in a glass of water looks bent. It's like it breaks at the surface. That's refraction too, right?
You bet. It's all because of how our brains interpret light. We instinctively assume that light travels in straight lines. But when light comes from water into air, it bends away from the normal. So when those rays reach your eye, your brain traces them back in a straight line, and that makes the underwater part of the straw look higher than it actually is. That's why things underwater always seem shallower than they really are. The book even gives the equation. Apparent depth equals real depth divided by the refractive index of water.
Makes sense. I guess that explains all those times I've stepped into what I thought was a shallow puddle and got soaked. Okay, time to get into something really cool. Total internal reflection. It sounds kind of spy movie-ish.
Oh, it totally is. It's all about light, trying to escape from a denser material into a rarer one, like from water into air. Remember, in that case, the light bends away from the normal. Now imagine you keep increasing the angle at which the light hits the boundary from inside the water. As you do that, the angle of refraction in the air also keeps increasing.
So the light is getting bent more and more away from the normal.
Exactly. And eventually you reach a special angle called the critical angle, where the refracted ray just grazes the surface. It's basically at a 90-degree angle. Beyond that critical angle, something wild happens.
What? The light just does a U-turn?
Pretty much. The light can no longer refract into the air. Instead, all of it is reflected back into the water. That's total internal reflection. And the amazing thing is, there's practically no loss of light intensity during this reflection. It's like a perfect mirror, but internal to the material.
Wow, that's way better than those regular mirrors where some light always gets absorbed.
Oh, for sure. And the condition for this total internal reflection is simple. The angle of incidence has to be greater than the critical angle. The book gives the equation. The sine of the critical angle equals the refractive index of the rarer medium with respect to the denser one. And that refractive index will always be less than 1 in this scenario.
Okay, and this critical angle is different for different materials, right? The book shows a table. For water to air, it's about 48.75 degrees, but for diamond to air, it's a much smaller 24.41 degrees. I wonder, could that be why diamonds sparkle so much? Like, light gets trapped inside and bounces around a lot before it can finally escape.
You're exactly right. Diamonds are cut in a way that maximizes the chances of total internal reflection. The light enters the diamond, but it keeps bouncing around inside because of the small critical angle. It's like a light show in there. And that's what gives diamonds their brilliance. The book even talks about some fun experiments you can do to see total internal reflection for yourself, like shining a laser pointer into a container of water. If you increase the angle, you'll see the light go from partial reflection and refraction to total internal reflection.
Cool. And they also mention how you can shine a laser through a long, cloudy test tube and see the light getting piped along by total internal reflection. It's like those fiber optic cables that carry our internet.
Exactly. Optical fibers work on the same principle. They're made of super pure glass or plastic with a core and a cladding. The core has a slightly higher refractive index, and the cladding has a slightly lower one. So when light enters the fiber at a steep enough angle, it undergoes total internal reflection at the core cladding boundary and keeps bouncing along inside the fiber, traveling long distances with very little loss. It's amazing.
It's mind-blowing to think that all our data is zipping around the world inside these tiny glass threads, bouncing off the walls thanks to total internal reflection. And the book even says these silica glass fibers are incredibly transparent. Like 95% of the light survives a journey of a kilometer. That's
Oh,
crazy.
right. Imagine trying to shine a regular flashlight that far. And optical fibers aren't just for communication either. They're used in medicine for endoscopy, to see inside the body without major surgery. And they're used in all sorts of sensors and decorative lights, too. It's a really versatile technology.
Okay, we've seen how light bends when it reflects and refracts at flat surfaces, and how prisms use total internal reflection. Now let's talk about bending light with curved surfaces, specifically spherical surfaces and lenses. This is where we start getting into the real business of focusing light to create images.
Absolutely. So a spherical refracting surface, it's basically a curved boundary between two materials that have different refractive indices. Just like a spherical mirror, it has a center of curvature and a radius of curvature. And just like with mirrors, we can use those paraxial rays, those rays that are close to the axis, to make things simpler. By applying Snell's law at this curved boundary and doing a bit of math, we can figure out a relationship between the object distance, the image distance, the refractive indices, and the radius of curvature. It's the foundation for understanding how lenses form images.
The book gives an example of light passing through a curved glass surface. And by plugging in all the values, the refractive index of air and glass, the radius of curvature, and where the light source is, you can calculate exactly where the image will form. It's like magic, but it's just physics. Now, a lens is basically two of these spherical refracting surfaces put together, right?
That's right. We can think of it like a double whammy of refraction. The light hits the first surface and bends, forming a temporary image. Then that temporary image acts as the object for the second surface, which bends the light again to form the final image that we actually see, or that gets focused on a camera sensor or whatever.
So it's refraction, then more refraction.
Exactly. And if we apply that spherical surface equation twice, once for each surface of the lens, and assume the lens is thin, we get a very useful formula called the lens maker's formula.
The lens maker's formula sounds like something straight out of a physics textbook.
It kind of is. The lens maker's formula tells you how to design a lens to have a specific focal length. It goes like this. 1f is the focal length, n sub 2 is the refractive index of the lens material, n sub 1 is the refractive index of the surrounding medium, usually air, and r sub 1 and r sub 2 are the radii of curvature of the two lens surfaces. Lens makers use this formula to calculate what shape to make the lens to get the focusing power they need. It's like having a blueprint for bending light.
So they can literally sculpt the path of light. That's pretty amazing. And once we have a lens with a particular focal length, there's another important equation that relates the object distance, the image distance, and the focal length, right? Similar to the mirror equation.
Exactly. It's called the thin lens formula, and it's very similar to the mirror equation, but with one key difference. 1v1 u equals 1f. See that minus sign? That's the difference. But again, u is the object distance, v is the image distance, and f is the focal length. And this formula works for both convex lenses, those are the ones that bulge outwards and converge light, and concave lenses, those cave inwards and diverge light. And it works for both real and virtual images. As long as you're careful with your sign conventions, you're good to go.
All right, minus sign noted. Now, lenses also have focal points, right? Just like mirrors. But with lenses, there are two of them, aren't there? One on each side.
It's exactly. They're called the first focal point and the second focal point. And they're located at equal distances on either side of the lens, right along the principal axis. The first focal point, sometimes labeled F, is on the same side as the object. And if you put an object right at that point, the rays that come out of the lens will be parallel. Think of it like the parallel output point.
Okay, got it.
The second focal point, usually labeled F', is on the other side of the lens. And for a convex lens, if parallel rays come in, they'll converge at that point. For a concave lens, they'll look like they're diverging from that point. That's the focus input point.
Those labels help, parallel output, and focus input. Makes a lot of sense. Now, just like with mirrors, there are some handy ray tracing rules for lenses too, right? Ways to figure out where the image will be formed.
Absolutely. There are three main rules for ray tracing with thin lenses. These are shown in figure 9.17 in the book. The first rule: a ray that comes in parallel to the principal axis, after passing through the lens, it'll go through the second focal point for convex lens, or it'll look like it came from the first focal point for a concave lens.
Makes sense. What's the second rule?
The second rule is super easy. Any ray that goes straight through the center of the lens, that's the optical center, it doesn't bend at all. It just keeps going straight.
Straight through the middle, no bending. Got it.
And the third rule, it says that a ray passing through the first focal point, or aims at it for a concave lens, will come out of the lens parallel to the principal axis. It's like the reverse of the first rule. So just like with mirrors, you only need to draw any two of these special rays, and boom, you can find the image location.
It's like connect the dots for light. Okay, and the magnification for lens is also a simple formula, right? M equals V. It's just the image distance divided by the object distance. No negative sign this time, but the sign still matters. Positive mem means the image is upright. Negative mem means it's inverted.
Exactly. Now, speaking of lenses, the book talks about this fun example of a magician seemingly making a glass lens disappear in a liquid. How do they do that? It's all about refractive index.
Okay, spilled secret.
To make the lens vanish, the magician uses a liquid that has the same refractive index as the glass the lens is made of. When that happens, light doesn't bend at all when it goes from the liquid to the glass or vice versa. The lens basically becomes invisible because it's optically the same as the liquid. It's like trying to see a piece of clear ice in a glass of water.
Sneaky. So it's not magic, it's just clever optics. And speaking of clever optics, the book talks about the power of a lens, and it's measured in diopters, which always sounded kind of mysterious to me.
It's not that complicated, really. The power of a lens just tells you how strongly it can converge or diverge light. A lens with a shorter focal length bends light more, so it has more power. The formula is simple. Power equals 1 divided by the focal length, but the focal length has to be in meters, and the unit is the diopter, which is just 1 inverse meter.
Okay, so a more powerful lens has a shorter focal length and bends light more. Makes sense. What happens if you stack multiple lenses together? Do their powers combine?
They do. If you put several thin lenses right next to each other, the combined power is just the sum of the individual powers. And this is really useful in designing complex optical instruments. Like cameras, microscopes, and telescopes often use multiple lenses to get the exact focusing and magnification they need. It's like a team effort for bending light.
So it's like combining multiple magnifying glasses, but way more sophisticated. Now let's talk prisms. We all know that prisms can split white light into a rainbow, but
Yeah.
what's wave optics? Okay, so we are diving into the world of wave optics today. Really fascinating stuff. You sent over some really incredible physics notes, and I know you want to really make sure you've got this concept of light acting like a wave down pat. And that's exactly what we're going to do today.
I think these notes you provided are fantastic. They lay out really clearly how our view of light has changed over time, almost like a detective story. Trying to figure out, Is light a bunch of tiny particles, or is it like ripples spreading through water?
Yeah, it really is kind of a mystery, isn't it? So we're going to rewind a bit and look at that very question. Is light a particle, or is it a wave? We'll look at the big ideas, those really important experiments, and by the time we're done, you'll have a solid grasp on wavefronts, Huygens Principle, and all that. We'll even tackle why light bends, why it bounces back, how it makes those awesome rainbow patterns, and we'll do it without getting bogged down in a ton of math. Ready to go. All right, let's get started.
Let's kick things off with how folks initially thought about light.
Ah,
Your notes mention that way back in the 17th century, there was this guy named Descartes.
yeah, Descartes.
He was one of the first to suggest that light might be made up of these tiny particles, kind of like super tiny balls flying around.
Like little bullets of light.
Right, exactly. And this idea really gained traction thanks to Isaac Newton. Remember his book, Optics?
Oh, yeah, super famous.
I mean, when Newton spoke, people listened. He really fleshed out that particle idea.
He kind of had a good track record.
Yeah. And honestly, it worked pretty well to explain some basic stuff, like reflection, light bouncing off a mirror.
Makes sense.
And it even explained refraction. That's when light bends as it passes from one thing to another, like from air into water.
Like when you stick a straw in a glass of water and it looks all bent.
Exactly.
Okay, so in this particle world, light is basically ricocheting off mirrors. And when it hits the water at an angle, these particles get sort of nudged off course, making it look like they bend.
That's the idea. Now, here's a super important point. This particle model, it actually made a very specific prediction. It said that if light bends toward that line that's perpendicular to the surface, we call that the normal, by the way.
Okay, the normal.
So if light bends toward the normal when it enters something new, like water, the particle theory says that means the light must be traveling faster in that second material.
So faster in the denser stuff if it bends that way. Got it.
Now, jump ahead to 1678, and along comes Christian Huygens.
Another big name.
He had a totally different take on light. He said, forget particles, light's a wave.
Wave theory.
Yeah. He imagined light spreading out like, say, ripples you see when you drop something in a pond.
Okay.
And the wild part is, his wave idea could also explain both reflection and refraction.
So instead of tiny particles bouncing or changing course, you've got these waves kind of interacting with the surfaces.
Exactly.
How did that explain the whole light bending thing, the refraction?
Okay, so Huygens pictured every single point on a wavefront. Imagine a line connecting all the crests of a wave at one instant, acting like it's sending out its own little wavelets. These wavelets spread out in all directions.
Mini waves.
Exactly. Now, when this wavefront hits a different material, like going from air into water, some parts of the wavefront will enter the new stuff first.
They get a head start.
And they'll either speed up or slow down, depending on the material.
Okay.
But the other parts of the wavefront are still back in the first material, moving at their original speed.
Right, so they're out of sync.
Totally.
Oh.
So because one section is moving at a different speed, the entire wavefront pivots as it crosses the boundary. It bends.
Like a marching band, right?
I like it.
You know, where one side of the band hits a muddy patch and slows down, so the whole line has to turn.
Exactly like that. That's a perfect analogy. And here's the really mind-blowing part. Huygens' wave model predicted the exact opposite of what Newton's particle model predicted.
Oh, this is getting juicy.
It said that if light bends toward the normal, it means the light is actually traveling slower in the second material.
Wait, hold up. So one says faster, the other says slower. That's a pretty big difference of opinion.
Huge. You've got two totally different explanations for what light even is, and they make completely opposite predictions about how it behaves.
So how did they figure out who was right? That seems like a stalemate.
Well, at first, Newton's reputation carried a lot of weight. Plus, the wave theory had this big problem.
Uh-oh.
If light is a wave, what exactly is waving? Especially when it travels through space, where there's nothing there.
Right, like a sound wave needs air to travel.
Exactly. People just couldn't wrap their heads around a wave without something to actually wave in.
Yeah, that's tricky.
So the wave idea kind of got sidelined for a while. But then, boom, 1801, Thomas Young enters the scene.
Cue dramatic music.
This guy was brilliant. He did this experiment that was a total game changer. It's the famous double-slit experiment.
Oh yeah, I've heard of that. But wait, didn't we just say you can't just use any two light sources? They have to be in sync?
Exactly. That's what made Young's experiment so clever. He found a way to get two light sources that were perfectly in sync, what we call coherent sources.
Okay, how do you pull that off?
He used just one light source and shone it through a teeny tiny pinhole.
Okay.
The light that came out of that pinhole then hit a screen with two more closely spaced pinholes.
So 2 sets of pinholes.
Right. Now, the light coming out of those second two pinholes, they're basically twins. They both came from that same original source, so they're always doing the same wiggle at the same time.
They're dancing in sync. Got it.
Exactly. Now, these two pinholes act like our coherent sources. They each send out their own waves, and those waves spread out and overlap on a screen behind them.
And what happens on the screen?
Magic. You see a pattern of bright and dark bands. It's called an interference pattern, and it's a dead giveaway that you're dealing with waves.
So like when you throw 2 rocks into a still pond and those ripples spread out and bump into each other.
Yeah, perfect analogy. Some spots get extra choppy because the waves add up, while others get smooth because the waves cancel out.
And light does the same thing. That seems like pretty strong evidence for the wave theory.
It was a knockout punch. And by measuring how far apart those bright and dark bands were, Young could even calculate the wavelength of light. And get this, the wavelength of visible light is ridiculously small. For example, yellow light has a wavelength of about 0.6 micrometers.
Whoa, how small is that?
I mean, we're talking less than a millionth of a meter.
That's mind-bogglingly tiny.
It is. And that teensy wavelength actually explains why we normally see light traveling in straight lines. We call this geometrical optics. It's kind of like a simplified way to look at light.
So it's like for everyday stuff, those wave-like effects are just too small to notice easily.
Exactly. Geometrical optics is great for designing glasses or figuring out how shadows work. We can just pretend light travels in straight lines.
Makes sense. So Young's experiment basically settled it. Light's a wave.
Case closed.
But we still haven't addressed that problem of what's actually waving if light can travel through empty space.
Right, that was still a head-scratcher.
Mm.
But don't worry, along comes James Clerk Maxwell in the mid-1800s with his theory of electromagnetism. This guy was a genius.
Another one.
Oh yeah, he basically figured out the rules of electricity and magnetism. And while he was working on this, he found something incredible hiding in his equations.
Mm.
They predicted these things called electromagnetic waves.
Electromagnetic waves. Sounds kind of complicated.
It's a bit more abstract, but here's the gist. These waves are made from changing electric fields and magnetic fields.
Okay.
A changing electric field makes a magnetic field, and a changing magnetic field makes an electric field. It's like a constant back and forth.
It's like a dance.
Exactly. And this dance can happen in empty space, no problem. No need for any stuff to wave in.
Whoa, so light is like a ripple in the electromagnetic field itself. That's wild.
It is. And get this. When Maxwell calculated the speed of these electromagnetic waves, he got a number that was almost exactly the speed of light.
No way.
Yep. That's when he realized that light is an electromagnetic wave.
Mystery solved. We know light is a wave, and now we know what kind of wave it is.
Exactly. Plus, Maxwell showed that these electromagnetic waves are transverse waves. That means the electric and magnetic fields are doing their dance perpendicular to the direction the wave is traveling.
Like shaking a jump rope, right?
Yep. The wave goes down the rope, but the shaking is up and down.
Perfect.
And just to make sure everything was crystal clear, later on, Heinrich Hertz actually produced radio waves in his lab.
Yeah.
Those are just another kind of electromagnetic waves.
Proof positive. What an amazing journey. From tiny particles to self-propagating electromagnetic waves. Okay, so now that we know light is a wave, let's get back to that Huygens' principle. How does that help us visualize how waves move?
Huygens' principle is all about those wavefronts. Remember, that's like taking a snapshot of all the crests of a wave at one moment. It helps us figure out how those wavefronts change shape and move through space over time. Imagine a light bulb shining in all directions.
Got it.
The wavefront spreading out from that bulb would be like expanding spheres, right?
Like a bubble growing bigger, a spherical wave.
Exactly. But if you're really far away from the bulb, a tiny part of that giant sphere will look pretty flat. We call that a plane wave. Like the light from a distant star, by the time it reaches us, it looks like a flat wavefront.
Okay, spherical, up close, flat, far away.
Now, how does Huygens' principle tell us where that wavefront is going next?
Okay, imagine each point on the wavefront acting like a tiny source that sends out little wavelets in all directions. These wavelets travel at the same speed as the original wave.
Each point is making its own mini waves.
Exactly. Now, to see where the wavefront will be a moment later, draw a line that touches the outer edge of all those little expanding wavelets. That new line is your new wavefront.
So it's like a bunch of dominoes falling in a row. Each domino knocks over the next one. I love that. And well, the back wave problem is a bit of a hiccup. A more advanced understanding of waves clarifies why it's not an issue in practice.
So we can basically use this principle to see how a plane wave keeps moving forward as a plane wave. Got it. Now, what happens when these waves hit something new, like a boundary between air and water? That's where things start bending and bouncing, right?
Exactly. Let's start with refraction, that bending of light when it changes speed. You remember Snell's law?
Vaguely. Something about signs of angles.
That's the one. N1 sin, I equals N2 sin R, where N1 and N2 tell us how much the speed of light changes in each material.
Okay.
We call that the refractive index. I is the angle of the incoming light, and R is the angle after it bends.
So how does Huygens' principle fit into this?
Picture a wavefront hitting the surface at an angle. As the wavefront crosses over, the part that enters the second material first immediately changes speed.
It either speeds up or slows down.
Right. But the rest of the wavefront is still back in the first material, moving at its original speed. Because they're moving at different speeds, the wavefront pivots. It bends.
Like our marching band in the mud.
Exactly. And if you carefully think about the geometry of the wavefront and those little wavelets, you can actually derive Snell's law.
So it's all based on how those mini waves interact at the boundary.
And remember that disagreement about the speed of light?
The particle versus wave showdown.
Right. Well, experiments showed that the wave model was right. Light does slow down in denser materials.
I always thought it would speed up.
Nope. Denser material, slower light. And that speed change also affects the wavelength.
Oh, right. Wavelength is basically the distance between two wave crests.
Yeah. When the speed changes, the wavelength changes too. But the frequency stays the same.
So the wavefronts get squeezed together if the speed decreases, but the number of them passing a point per second remains constant. That's the frequency.
Yeah.
Okay, so wavelength changes, speed changes, but the frequency and therefore color stay the same? Hey, by the way, why did the light wave break up with the prism?
Why?
It felt refracted.
Nice one.
Ah.
All right, so what happens when light goes from a denser material to a less dense one?
Bro.
Say, from water back into air.
Well, based on our marching band analogy, I'd say the light should bend away from the normal.
You got it. And if the incoming angle gets big enough, there's a point where the light basically skims along the surface. We call that angle the critical angle.
Critical angle. Got it.
And if you crank that angle up even further, past the critical angle, total internal reflection, all that light gets bounced back into the denser material.
Like a perfect mirror.
Exactly. It's like a light trap. And that's the principle behind fiber optics, by the way.
Right. The light stays trapped inside the fiber. So cool. Now, what about regular reflection? How does Huygens' principle explain that?
Same idea. Imagine a wavefront hitting a mirror. As it touches the surface, each point sends out those little secondary wavelets.
Spreading the love.
They spread back into the same material at the same speed. If you draw that line connecting all those wavelets, you'll see that the reflected wavefront bounces off the same angle it hit the surface.
Angle in equals angle out.
Boom. That's the law of reflection, explained by waves.
So Huygens' principle helps us see how light bends, bounces, and even how prisms and lenses work. It all comes down to how the speed changes and reshapes the wavefront.
Absolutely. For example, a prism splits white light into a rainbow because each color of light travels at a slightly different speed inside the glass.
That's why we see all the colors spread out.
Right, and lenses, well, they're shaped to either focus light to a point or spread it out, all by changing the shape of the wavefront.
It's amazing how much we can explain just by understanding how waves behave.
Hmm.
Okay, let's move on to another cool wave effect, interference. This is where things really get interesting.
It's all about what happens when waves meet and mingle. The key principle here is superposition.
Superposition, right. If two waves are in the same spot, their effects add up. Exactly. Crest meet crest, you get a bigger wave. Crest meets a trough, they cancel each other out.
So you can get brighter light or dimmer light, depending on how the waves line up.
Now, to get those really clear interference patterns with light, we need coherent sources. That means their waves have a constant phase relationship. They're always doing the same wiggle at the same time.
Okay, so coherent means in sync.
Exactly. If the phase difference stays constant, then the interference at any point will always be either constructive or destructive.
Okay, break that down for me.
So if the path difference between two waves is a whole number of wavelengths, meaning one wave traveled one whole wavelength further than the other, they arrive perfectly in sync.
Crests meet crests, troughs meet troughs.
Exactly. That's constructive interference, and you get a super bright spot.
And if the path difference is off by half a wavelength,
That a crest from one wave meets a trough from the other, and they cancel out.
destructive interference. Dark spot.
You got it.
And for anything in between, you get something in between bright and dark.
Now, what if those light sources aren't coherent? Like two regular light bulbs.
Well, their waves would be all over the place, right?
Right. The phase relationship would be constantly and randomly changing, so no stable interference pattern.
That's why we don't see interference patterns everywhere.
Exactly.
Those ripple tank diagrams in the notes really help me picture how this works. It's like those waves are colliding and making these amazing patterns.
Visualizations are super helpful.
Big time. Okay, so how did Young prove that light was a wave using this interference thing?
With the double slit experiment, of course. But remember, he needed coherent sources.
Right. Regular light bulbs wouldn't cut it.
So what he did was super clever. He shone a single light source through a tiny pinhole. Then that light hit another screen with two more pinholes close together.
A pinhole sandwich.
Exactly.
Hmm.
And the light coming out of those second pinholes, they were essentially clones. They came from the same source, so they were always in sync. Coherent. It was. And when those coherent waves from the two pinholes spread out and overlapped, they created a clear interference pattern on the screen behind them. Bright and dark bands, perfectly spaced.
Game, set, match for the wave theory.
Pretty much. And he even used those measurements to calculate the wavelength of light, confirming just how incredibly tiny it is.
Unbelievably small.
Right. Okay, so we've talked about how waves add up and cancel out. Let's move on to another cool wave trick. Bending around corners, also known as diffraction.
Like when you can hear someone talking around a corner, even if you can't see them.
Exactly. Diffraction happens with all kinds of waves, light included. It's the spreading out or bending of waves when they encounter an obstacle or squeeze through a narrow opening.
But we don't see light bending around corners all the time, do we?
It's all about scale. The amount of bending depends on the size of the wave compared to the size of the obstacle or opening. Light waves has such tiny wavelengths that for everyday objects, the diffraction is really subtle, hard to notice. But if you look at really small things like through a microscope, or you're trying to get a super sharp image with a telescope, then diffraction starts to matter a lot.
It sets a limit on how much detail we can see.
Right. And remember those pretty colors on a CD?
Oh, yeah.
Diffraction again. Those tiny grooves on the CD act like a diffraction grating, splitting the light into its different colors.
Wow, so many things we see every day are actually caused by these wave effects. So we talked about interference with two slits. What happens if you just have one slit?
Single slit diffraction is its own thing. Instead of those evenly spaced bright and dark fringes, you get a different kind of pattern. There's a big bright central band and then weaker dark and bright bands on either side.
Not as evenly spaced.
Nope. So imagine light hitting a single narrow slit. Every point in that slit acts like a tiny source of wavelets.
Okay.
Now think about the light traveling at slightly different angles from different points across the slit.
Those slight differences in angle mean the waves travel slightly different distances to reach the same point on the screen.
Exactly. And those tiny differences in distance lead to interference.
Even though they came from the same slit.
Yep. It turns out that in the middle, right behind the slit, the waves all arrive pretty much in sync. So it's super bright.
Makes sense.
But then, at specific angles, waves from different parts of the slit will be out of sync by exactly half a wavelength.
Destructive interference, dark spot.
You got it. And those weaker bright bands, those are where the waves aren't perfectly in sync, but aren't totally out of sync either.
So it's like a gradient of brightness, with the middle being the most intense?
It's a different kind of pattern, but still all because of those tiny waves interfering with each other.
Now, Richard Feynman had a really interesting take on this whole interference versus diffraction thing. He said it's not about two separate things, it's more like a spectrum. Two sources, we call it interference. A whole bunch of sources, we call it diffraction. It's all about the number of waves mixing together.
He was a brilliant physicist with a knack for seeing the bigger picture. And you know, the double slit experiment we talked about earlier, that's actually a combination of both single slit diffraction from each slit and the interference between those two slits. Two effects happening at the same time.
Mind blown.
Speaking of mind-blowing, you know, you can actually see single slit diffraction at home. All you need are two razor blades and a light bulb.
No way. Really?
Totally. Just hold the razor blades really close together so they make a tiny slit, then look at a light bulb filament through that gap. You should see those diffraction fringes. Bright and dark bands running parallel to the blades.
I am so trying this later.
We should.
The notes mentioned using colored filters could make it even clearer.
Yeah, different colors will diffract differently. And the fact that we can see this with such simple things, it really drives home that light is a wave.
And you know what else is cool? energy is never lost or created in these interference and diffraction patterns. It's just moved around. The dark spots have less energy, the bright spots have more.
Exactly.
Yeah.
Energy is conserved. Okay, ready to tackle the last big topic in wave optics. Polarization.
Bring it on. This is about the direction of the light wave, right?
Right. Polarization is a property you only see with transverse waves. Remember our rope analogy? Shaking it up and down versus side to side.
Yeah.
That's like a linearly polarized waves. All the vibrations are happening in a single plane. Light waves are also transverse, and they can be polarized too.
Now, normal light, like from the sun or a light bulb, its electric field is vibrating in all sorts of directions. It's unpolarized.
Like a bunch of jump ropes all being shaken in random directions. Now imagine passing that light through a special filter, a Polaroid filter.
Like polarized sunglasses.
Exactly. These filters have long molecules all lined up in one direction. They act like a gate, only allowing light waves vibrating in a specific direction to pass through. We call that direction the pass axis. The light that comes out is now polarized.
So it's like it's been combed, so all the waves are vibrating the same way.
Perfect analogy. And if you put a second Polaroid filter behind the first one, things get really interesting. When the pass axes of both filters are aligned, the light passes through. No problem.
Okay.
But as you rotate that second filter, less and less light gets through.
It's like closing the blinds.
And when the pass axes are perpendicular, at 90 degrees, almost no light gets through at all. It's like someone flipped a switch and turned off the light.
That's so weird.
But it proves that light is a transverse wave.
And there's a law that describes how much light gets through, right? Malice's law?
You got it. It says that the intensity of the light after the second filter is the original intensity times cosine squared of the angle between the filter's pass axis.
So at 0 degrees, all the light gets through. At 90 degrees, no light. Makes sense.
Now here's a fun one. What happens if you put a third Polaroid between two crossed Polaroids angled at 45 degrees?
I'm not sure.
Some light actually gets through the whole system. Pretty wild, huh?
That is super counterintuitive. So polarization isn't just a theoretical curiosity, it has real uses. You mentioned polarized sunglasses. What else?
Oh, tons of things. LCD screens, camera filters, even 3D movies all rely on polarization.
It's pretty amazing how something so fundamental can lead to such a wide range of applications. Hey, why was the photon so well behaved?
I don't know why.
Because it was polarized.
You got me there.
That's a good one.
It is.
Well, we covered a lot of ground today. From arguing about what light even is to controlling its direction with polarization, it's been quite a journey.
It really highlights the power of scientific thinking, going from a simple observation to a completely new understanding of how the universe works.
Absolutely. And it makes you wonder what other mysteries are out there, just waiting to be unraveled.
Who knows what incredible discoveries are still to come? We might even have to rethink our understanding of light again someday.
That's the beauty of science, right? It's a constantly evolving story.
Exactly. And who knows, maybe you'll be the one to make the next big breakthrough.
Well, on that note, we'll wrap things up here. Hopefully, this deep dive into wave optics has left you feeling a little more enlightened and maybe even inspired to explore some of these ideas further. What new questions has this sparked for you? We always love to hear from our listeners. Okay, so today we are deep diving into Chapter 11, Dual Nature of Radiation and Matter.
Ooh.
It's a mouthful, right?
Yeah.
Dual nature, radiation, and matter. It sounds like something straight out of like a sci-fi novel or something.
Right. A little intimidating maybe for some folks, but...
Yeah, but honestly, the concepts in here are even more mind-bending than any sci-fi I've read recently.
Absolutely. And it's really fundamental to understanding how the universe works at its most basic level.
Yeah, and, we might think we have light figured out, right? I mean, we use it every day. We kind of take it for granted.
Right. We'll flip a switch, the lights come on. That's like magic.
Exactly. But back in the day, the late 1800s, scientists were pretty confident that they had light all figured out thanks to guys like James Clerk Maxwell and Heinrich Hertz.
Yeah, they really laid the foundation for our understanding of electromagnetism and the wave nature of light.
Yeah, Maxwell's equations, they're like these elegant mathematical statements that describe how electricity and magnetism are intertwined and how they give rise to these self-propagating waves that we call light.
Right. And Hertz's experiments were crucial. He actually generated and detected these electromagnetic waves in the lab, confirming Maxwell's theories.
Yeah, so by the end of the 19th century, the wave nature of light seemed like a done deal. It explains so much like how light bends around corners or how it creates those cool interference patterns when you shine it through two slits.
Right, diffraction and interference, classic wave behaviors.
Exactly. But then science being science decided to throw a curveball.
Always keeping us on our toes, right?
Yeah. So along comes this new area of research, electric discharges in gases.
This is where things start to get really interesting. You've got these glass tubes filled with gas, and you apply a high voltage across them, and all sorts of cool stuff starts to happen.
Yeah, like you get these beautiful glowing colors depending on the gas you're using. It was a big scientific fad back then.
Like lava lamps for physicists.
Exactly. But it wasn't just pretty lights, it was also a goldmine of new discoveries. In 1895, Wilhelm Röntgen stumbles upon these mysterious rays that could pass through solid objects. He calls them X-rays.
Totally by accident, too. He was experimenting with cathode rays and noticed that a screen across the room was glowing, even though the tube was covered in black cardboard. It's like finding a secret passage in your house.
Yeah, a total game changer in both physics and medicine.
Right. Suddenly we could see inside the human body without surgery. It was revolutionary.
And then, just a couple of years later, J.J. Thomson starts playing around with those same cathode rays, the ones that cause the glow in the discharge tubes. He was a master experimenter.
And this is where the story of the electron really begins, right?
Yeah, Thomson being Thomson, he's like, okay, let's see what happens if I apply electric and magnetic fields to these cathode rays.
And lo and behold, he finds that he can deflect them.
Exactly. And not only could he deflect them, but by carefully measuring how much they bent in those fields, he could calculate their speed and their charge to mass ratio.
Which is basically how much electric charge they carry compared to how much mass they have.
Right. And here's where it gets really mind-blowing. The speed he measured for these cathode rays was incredibly fast, a significant fraction of the speed of light. And the charge to mass ratio he calculated was always the same no matter what metal he used for the cathode or what gas he put in the tube.
That was the real eureka moment. That consistency across different materials was a huge clue.
Yeah, it was like screaming, hey, this is something fundamental. It's not just a quirk of the experiment. It's a universal building block.
Precisely. It suggested that these cathode rays weren't just some random property of the gas or the metal. They were something intrinsic to matter itself.
Yeah, like a fingerprint revealing a common origin. And get this, around the same time, other scientists were noticing that if you shine ultraviolet light on certain metals or even just heat them up, they'd start spitting out negatively charged particles.
And guess what? Their charge-to-mass ratio was exactly the same as Thomson's cathode rays.
It was like the universe was whispering, these are all connected.
It's like solving a puzzle and suddenly realizing that 3 different pieces fit together perfectly.
Exactly. So Thomson puts 2 and 2 together, and in 1897, he announces to the world, hey, everyone, these are all the same thing. And they're these tiny, negatively charged particles that are a fundamental part of all matter. I'm going to call them electrons.
And thus the electron was born. Pretty momentous occasion.
Huge! And he snags a well-deserved Nobel Prize for this discovery in 1906. But here's the thing. At this point, they only knew the ratio of charge to mass for an electron. They didn't know the actual charge of a single electron.
Right, it's like knowing the density of a material, but not the actual mass or volume.
Yeah, you need that one crucial piece of information to complete the picture.
Yeah.
So fast forward a few years and enter Robert Millikan with his super clever oil drop experiment.
Oh, this is one of my favorite experiments of all time. It's so elegant in its simplicity.
Yeah, it really is. So picture this Millikan's got this little chamber filled with air. He sprays in these tiny, tiny droplets of oil like a fine mist.
And some of these droplets, as they're floating around, would naturally pick up a few stray electrons from the air, just by random chance.
Yeah, and then he'd apply an electric field across the chamber, so there's these charged plates at the top and bottom, creating this electric force that could push or pull on the charged oil drops.
Right, and by very carefully adjusting the strength of that electric field, he could actually make those tiny oil drops hang suspended in midair.
Like balancing a feather on your nose, it sounds almost impossible.
It was incredibly challenging.
Mm-hmm.
It took years of meticulous work and some ingenious experimental design.
Yeah, but he pulled it off. And here's the key insight. By measuring the exact electric field needed to suspend different oil drops with different charges, he realized that the charge on each droplet was always a multiple of the same tiny fundamental unit of charge.
Around 1.602 times 10 to the minus 19 coulombs. That's a tiny, tiny amount of charge.
Yeah, it's like the smallest possible coin of electric charge. You can't have fractions of this amount. It's quantized.
A profound realization. Electric charge isn't like water that you could pour in any amount. It comes in these discrete little packets.
And once they had this fundamental unit of charge, which we call D, and Thomson had already given them the charge to mass ratio E over m, they could finally calculate the actual mass m of a single electron.
It's like knowing the price of one cookie and how many cookies you get per dollar. You can finally figure out how much a dollar is worth.
Exactly. So thanks to these brilliant experiments with glowing tubes and painstakingly balancing tiny oil drops, we started to get a real picture of these amazing little particles called electrons.
These fundamental building blocks of matter.
Okay, so now we've got these electrons, these tiny negatively charged particles buzzing around everywhere. But how do they actually get out of something solid, like a metal? You mentioned earlier that metals have these free electrons that allow them to conduct electricity.
Right, so these free electrons, they're not bound to any specific atom. They're kind of like a sea of mobile electrons that can flow throughout the metal.
Yeah, but if they're so free, why don't they just all spontaneously zoom out of the metal, like an electron exodus?
That's a great question. It's because even though they're free to move around inside the metal, there are still attractive forces holding them in. They're attracted to the positively charged ions that make up the metal lattice.
Ah, so it's like they're at a party.
Yeah.
They can mingle and move around, but there's still a bouncer at the door preventing them from leaving.
Exactly. And to escape that bouncer, they need a certain amount of energy to overcome those attractive forces. This energy is called the work function. It's like an exit fee for electrons trying to leave the metal party.
Okay, so how do they pay that exit fee? How do they get enough energy to escape?
Well, there are three main ways to give them that energy. One is called thermionic emission. You just heat the metal up.
Like turning up the heat at the party.
Exactly. The increased thermal energy makes the electrons jiggle and vibrate more, and some of them gain enough energy to overcome that work function and escape the surface.
Makes sense. The hotter it gets, the wilder the party, the more likely someone is to bust out.
Exactly. And this is actually how those old vacuum tubes in vintage electronics worked. They'd heat up a filament, and electrons would boil off, creating a flow of current.
So that's how our grandparents' radios worked. Pretty cool.
Yeah, it's a classic example of thermionic emission in action. Another way to get electrons to escape is called field emission.
Sounds intense.
It is. You apply a really, really strong electric field to the metal. We're talking fields on the order of 10 to the 8th volts per meter. That's like an electric force field strong enough to rip electrons right out of the metal.
Like the bouncer got replaced by a giant vacuum cleaner sucking electrons out the door.
Pretty much. And this is used in things like electron microscopes, where you need a very fine beam of electrons to image tiny objects.
So those are two ways to give electrons the boot. Now what about the third way, the one that's the star of our chapter, photoelectric emission?
Yes. This is where light comes into play. When light of a specific frequency shines on a metal surface, it can transfer its energy to those electrons in the metal. And if an electron absorbs enough energy from the light, it can overcome that work function and get ejected from the metal surface.
So it's like light is shining a spotlight on a lucky few electrons and giving them a free pass out of the party.
Exactly. And these light-liberated electrons are what we call photoelectrons. But as we're about to see, the details of this photoelectric effect got really, really weird.
Yeah, it's like the universe decided to play a cosmic prank on physicists.
Always keeping things interesting. So the first hints of this peculiar effect actually popped up during Hertz's experiments with electromagnetic waves, way back in 1887. Remember, he was the guy who really nailed down that light as an electromagnetic wave.
Yeah, but even he noticed something strange going on.
Right. He was using a spark gap generator to create these electromagnetic waves and a loop of wire with a tiny gap to detect them. And he noticed that the sparks in his detector were stronger when ultraviolet light happened to be shining on the emitter part of his setup. It was like the UV light was giving those sparks an extra boost.
Like an invisible energy drink for sparks.
Yeah, something like that. He didn't fully understand why at the time, but it was a little clue that something interesting was going on.
Yeah, a little breadcrumb on the path to a major scientific revolution. So then between 1886 and 1902, two other physicists, Hallwachs and Lenard, started really digging into this photoelectric effect in more detail.
They used these evacuated glass tubes with two metal plates inside. One was the emitter, where the light would shine, and the other was the collector, where the electrons would go.
Yeah, and they could control the voltage between those plates to make it easier or harder for the electrons to flow.
Right. So when they shone ultraviolet light on the emitter plate, they saw a current flowing in the circuit, meaning electrons were being ejected from the emitter and traveling to the collector.
Makes sense, light hits. Metal electrons get kicked out, current flows. But then they discovered something really bizarre.
Yeah, that's when they found the threshold frequency. This was a huge clue that something wasn't quite right with the classical understanding of light.
Yeah, because for any given metal, if the frequency of the incoming light was below a certain threshold, absolutely no electrons would be emitted no matter how bright or intense the light was.
It was like there was a minimum energy requirement for the light to even budge those electrons. It was like trying to break a window with a tennis ball.
Right.
You can throw as many tennis balls as you want, but they're just not going to have enough energy to shatter the glass.
So you could shine a stadium floodlight of red light at some metals and not a single electron would care. But then a tiny little ultraviolet light could kick electrons out like they were on a trampoline.
Exactly. And different metals had different threshold frequencies. It was like
Yeah.
some metals were more picky about the color of light they'd respond to.
So clearly something more than just the intensity or brightness of the light was going on. Here's where they really started to probe the details of this photoelectric effect.
Yeah, they set up these experiments where they could very carefully control the intensity and the frequency of the light and the voltage between the emitter and collector plates.
So they could see how many electrons were being ejected, the photocurrent, and how much energy they had by measuring the stopping potential.
Right. And what did they observe?
Well, first, when they kept the frequency, the color of the light the same, and just made it brighter, increased the intensity, they found that the photocurrent increased proportionally.
Meaning more electrons were being ejected per second. That part made an intuitive sense, right? More light hitting the metal, more electrons getting knocked off.
Yeah, it's like if you throw more tennis balls at a wall, you'll hit it more often. But what happened when they started messing with the voltage between the plates?
This is where it gets really interesting. If they made the collector plate more and more positive, it would attract more of those emitted electrons.
Like a stronger magnet pulling in more paper clips.
Exactly. The photocurrent would increase until it reached a maximum value called the saturation current.
Meaning all the electrons that were being ejected were being collected.
Right. Everyone who left the party made it to the parking lot. But then they flipped the switch and made the collector plate negative.
Like putting up a keep out sign for electrons.
Exactly. Now, the collector was actively repelling those negatively charged electrons. Only the most energetic ones could overcome that repulsive force and make it to the collector.
So as they made the negative voltage stronger and stronger, the photocurrent would decrease.
Until at a certain voltage called the stopping potential, the photocurrent dropped to zero. Even the fastest electrons were being turned back.
Like a hill so steep that even the fastest runners couldn't make it up.
Precisely. And this stopping potential allowed them to directly measure the maximum kinetic energy of those emitted photoelectrons.
Yeah, they found that the maximum kinetic energy was directly proportional to the stopping potential.
Right, and here's the crucial part. While the saturation current did change with the intensity of the light, the stopping potential, and therefore the maximum kinetic energy of the electrons, stayed the same for a given frequency of light, no matter how bright the light was.
That's so weird. It's like the color of the light determined the speed limit for the escaping electrons, not how many light bulbs you were shining.
It's one of those wait what moments in physics that really makes you rethink your assumptions.
Yeah, it's like saying the color of a tennis ball determines how fast it bounces, not how hard you throw it.
Exactly. It's totally counterintuitive. So what happened when they changed the color of the light they were using?
Well, they found that different frequencies of light, but keeping the intensity the same, resulted in different stopping potentials. Higher frequency light led to a higher stopping potential, meaning the electrons were being ejected with more kinetic energy.
It was like the color of the light was a secret code that unlocked different speed settings for the electrons.
Yeah, and if you plotted the stopping potential versus the frequency of the light, you'd get a beautiful straight line. And that line had a starting point on the frequency axis, that threshold frequency we talked about earlier. Below that frequency, the line simply didn't exist, meaning no electrons were emitted at all.
It's like saying you need a key of certain color to even open the door to the electron party.
Exactly. So let's recap these mind-blowing experimental observations. Brighter light gives you more electrons, higher photocurrent, but it doesn't make them faster, same stopping potential. Higher frequency light makes the electrons faster, higher stopping potential, and there's a minimum frequency of light needed to eject any electrons at all, the threshold frequency.
It's like a set of rules for a very strange game.
So how did the well-established wave theory of light, the one that had explained so much, try to make sense of all this, and where did it fall flat on its face?
Well, the wave theory pictured light as this continuous wave spreading out like ripples in a pond. The energy of the wave was evenly distributed across its wavefront.
So the idea was that if you shine light on a metal, the electrons in the metal would gradually soak up that wave energy like a sponge absorbing water.
Right, the more intense the light, the more energy per second the electrons should absorb, and therefore the faster they should be ejected when they finally had enough energy to escape.
Yeah.
But that's not what the experiments showed at all.
Strike one for the wave theory. The maximum kinetic energy of the photoelectrons didn't depend on the intensity of the light at all.
It's like saying how wet a sponge gets. Depends only on the color of the water you're pouring on it, not how much water you're pouring.
Okay, strike one. What else did the wave theory get wrong?
Well, it also predicted that there shouldn't be a threshold frequency. If you just shone a dim enough light for long enough, the electrons should eventually soak up enough energy from the continuous wave to escape, regardless of the light's frequency.
Like a slow drip of water eventually filling up a bucket?
Exactly. But the experiments clearly show that wasn't the case. There was this hard cutoff below a certain frequency, no matter how long you waited.
Strike two. And the third strike. What finally knocked the wave theory out of the game?
The time delay. The wave theory predicted that it should take some time for an electron to absorb enough energy from the continuous wave to escape, maybe even hours for really dim light. But the experiments showed that photoemission was practically instantaneous, happening in less than a billionth of a second.
Like flipping a switch and the light comes on instantly.
Exactly. So the wave theory just couldn't account for these key experimental observations. It was time for a new way of thinking about light.
And that's where Einstein comes in, right? With his revolutionary and at the time quite controversial idea of light, quanta.
In 1905, Einstein published his groundbreaking paper on the photoelectric effect and proposed that light energy isn't continuous, but comes in these discrete little packets, these tiny bundles of energy that he called quanta.
And we now call them photons.
Right. Each photon carries a specific amount of energy, and that energy is directly proportional to the frequency of the light.
So instead of a continuous wave washing over the metal, it's more like a stream of tiny energy bullets hitting the surface.
Exactly. And Einstein said that in the photoelectric effect, a single electron absorbs a single photon. It's a one-on-one energy exchange.
So if the energy of that photon is greater than the work function of the metal, the electron gets ejected. If not, it stays put.
Precisely. And he came up with a simple but powerful equation to describe this. Kmax equals h nu minus phi naught, where Kmax is the maximum kinetic energy of the ejected electron, Hs. Planck's constant nu is the frequency of the light, and phi naught is the work function of the metal.
That equation beautifully explained all those weird experimental observations that had stumped the wave theory.
It was a game changer. It completely revolutionized our understanding of light.
So let's break it down a bit. The maximum kinetic energy of the electron depends on the frequency of the light, because that determines the energy of the incoming photon. It doesn't depend on the intensity of the light, because intensity is just the number of photons arriving per second, not the energy of each individual photon.
Right. It's like saying the speed of a bullet depends on the type of gun that fired it, not on how many bullets are being fired.
And photoemission can only happen if the energy of the photon is greater than the work function of the metal, which perfectly explains that threshold frequency.
It's like saying you need a key of a certain size to open a lock. Having more keys of the wrong size won't help.
And the instantaneous emission. That's explained by the fact that a single photon can be absorbed by a single electron incredibly quickly. It's a direct energy transfer, no waiting required.
It's like a perfect billiard ball collision. One photon hits one electron and boom, the electron flies off.
So Einstein's idea of light quanta explained the photoelectric effect flawlessly. But was it just a clever idea on paper, or was there actual experimental proof?
That's where Millikan comes back into the story. In a rather ironic twist, he set out to disprove Einstein's theory. He was a big believer in the wave theory of light and thought Einstein's idea was nonsense.
Oh, the irony. Trying to prove someone wrong and ending up proving them right. It's a classic tale in science.
Yeah, it happens more often than you might think. So Millikan meticulously measured the stopping potential for different frequencies of light shining on different metals.
Yeah.
And what did he find?
A beautiful straight line, just as Einstein's equation predicted.
Exactly. And the slope of that line was exactly what Einstein had predicted. It was equal to Planck's constant divided by the charge of an electron.
So Millikan unintentionally provided some of the strongest evidence for Einstein's theory of light quanta.
And for his meticulous work on the photoelectric effect and his earlier oil drop experiment. Millikan received the Nobel Prize in Physics in 1923. And of course, Einstein himself received his Nobel Prize in 1921. And the citation specifically mentioned his explanation of the photoelectric effect.
So this seemingly simple experiment with light shining on metal turned out to be one of the most important experiments in the history of physics. It completely changed our understanding of what light is.
It revealed the dual nature of light. It can behave like a wave and like a particle.
So light carries energy in these little packets called photons. Do photons also carry momentum like we associate with particles?
That was Einstein's next bold proposal.
Yeah.
He said, yes, photons do carry momentum. And the equation for that is P equals h nu over c, where P is the momentum. H is Planck's c. Planck's constant nu is the frequency of the light, and c is the speed of light.
So that further solidified the particle nature of light. These photons weren't just bundles of energy, they also had momentum, like tiny little projectiles.
And this wasn't just a theoretical idea. It was experimentally confirmed a few years later by Arthur Compton in his studies of how X-rays scattered off electrons.
So the photon picture of light was becoming very well established. And to summarize, radiation interacts with matter as these particles called photons, each with a specific amount of energy and momentum.
Right, and the intensity of light is just a measure of how many photons are arriving per second, not how much energy each photon has.
And photons are electrically neutral, so they're not affected by electric or magnetic fields, but they can transfer energy and momentum to charged particles like electrons.
It's a very different way of thinking about light than the classical wave picture.
And it leads to all sorts of interesting consequences. But here's the real mind blower. If light, which we thought was a wave, it can also behave like a particle, can particles like electrons also behave like waves?
Yes.
Yeah.
That's the question that Louis de Broglie pondered in the early 1920s.
Yeah.
And his answer was a resounding yes.
Talk about turning the tables. So if energy can have these particle-like properties, maybe matter can have some hidden wave-like behavior too.
Precisely. De Broglie was a brilliant French physicist who was really intrigued by this idea of symmetry in nature. He saw this duality emerging with light wave and particle, and he thought, why should it be limited to light? Maybe it's a fundamental property of everything in the universe.
So what was his reasoning behind this pretty radical idea?
Well, he started with Einstein's famous equation E equals mc squared, which shows that mass and energy are really just different forms of the same thing.
Yeah, that equation is like the rock star of physics.
For good reason. It's profound.
Yeah.
So de Broglie thought, if light, which is a form of energy, can behave like a particle, maybe particles which have mass, can also behave like waves.
And he came up with a way to describe this wave-like behavior of matter.
He did. He proposed that every particle with momentum also has a wavelength associated with it, and he came up with an equation to calculate that wavelength. It's now known as the de Broglie relation, lambda equals h over p, where lambda is the wavelength, h is Planck's constant, and p is the momentum of the particle.
So that little equation connects the wave property, the wavelength, to the particle property, the momentum, and it's all tied together by Planck's constant, that fundamental constant of the quantum world.
It's a beautiful equation. It's simple yet profound.
And if you apply that equation to a photon, you get back the wavelength of the light it represents, which is a nice consistency check.
Right. It shows that de Broglie's relation works for both matter and energy. So if I'm sitting here recording this podcast, do I technically have a wavelength?
Haha. Well, in theory, yes. According to de Broglie's equation, anything with mass and velocity has a wavelength. But for everyday objects like humans or podcasting equipment, the wavelengths are so incredibly tiny that they're practically meaningless.
It's because Planck's constant is such a ridiculously small number. When you divide it by the momentum of a macroscopic object, you get a wavelength that's smaller than the size of an atom.
So we don't notice our wave-like nature in our everyday lives.
But when you get down to the scale of subatomic particles like electrons, their wavelengths become significant and experimentally measurable.
Like in that example in the chapter, an electron moving at a typical speed in an atom can have a wavelength comparable to the size of the atom or even the wavelength of X-rays.
Exactly. That's why the wave nature of matter is so important at the atomic and subatomic level. It governs how electrons behave in atoms and how atoms interact with each other.
And for this groundbreaking idea, de Broglie received the Nobel Prize in Physics in 1929. It was a huge shift in our understanding of the universe.
It showed that the world is far stranger and more wonderful than we could have ever imagined.
So to wrap it all up, we've seen how these seemingly unrelated phenomena, like electric discharges, the glow of a glass tube, and the emission of electrons by light, are all deeply interconnected through these fundamental concepts of wave-particle duality. It's amazing how nature ties everything together at the most fundamental level.
It's a beautiful tapestry of interconnectedness. And it all started with those early experiments with light and matter.
And the realization that both light and matter can exhibit this dual nature, this ability to act like both a wave and a particle. It's a concept that's still mind-blowing, even a century later.
It challenges our everyday intuitions about how the world works and forces us to embrace a new way of thinking about reality.
So if everything has a wavelength, what does that really mean? How does this wave-particle duality shape the very fabric of the universe? That's something to ponder long after this deep dive is over.
It's a question that physicists are still grappling with today, and it leads to some of the most fascinating and mind-bending ideas in modern physics.
Well, that's all the time we have for today's deep dive. Hopefully, this has illuminated some of the mysteries of the dual nature of radiation and matter for you. Until next time, keep those quantum thoughts simmering.
Chapter 12. Atoms. We're diving deep into the building blocks of, well, everything. You guys sent in some seriously fascinating stuff about atoms, like how we went from having a vague idea about them to actually understanding how they work. It's like going from seeing a finished car to actually knowing how the engine works.
Yeah, and what's super interesting is where we start, like way back in the late 19th century. At that point, people were kind of getting on board with the idea that atoms existed, but nobody really knew what they looked like on the inside. Imagine trying to figure out how a clock works without even knowing it has gears.
Totally. It'd be like, well, there's this thing called a clock and it tells time
Mhm.
somehow. But back then, the first real clue came from J.J. Thomson's experiments in 1897. He was messing around with electricity zapping through gases and, well, you flagged this in your submissions. What was so groundbreaking about those experiments?
Well, those experiments revealed something pretty incredible. They showed that atoms, no matter what they were made of, all contained these tiny, negatively charged particles. They called them electrons. It was like discovering that all those different Lego bricks, no matter their shape or color, have that same little connector on top.
It's like finding a universal ingredient, right? So, okay, they've got these negative bits inside, but atoms as a whole, they don't have an electric charge, do they? They're neutral. What did that tell scientists about what else must be lurking inside the atom?
It meant there had to be something positive in there, too, to balance out the negative charge of the electrons. Otherwise, every atom would be like a tiny little lightning bolt zapping around. Like, you know those seesaws at the park? They need weight on both sides to stay balanced.
Makes sense.
Yeah.
It's like you can't have a negative without a positive to keep things in check. So based on that, Thomson came up with the first model of the atom in 1898. It was called the plum pudding model. Now, I know that might sound a bit weird. Can you break that down for us? Like, imagine you're explaining it to, I don't know, your grandma who's really into science but maybe hasn't kept up with the latest atomic fashion.
Okay, so picture this. You've got this positively charged pudding, kind of like a diffuse blob of positive charge, taking up most of the space. And scattered throughout this pudding are the negatively charged electrons, like plums or raisins stuck in the dough. That was Thomson's idea, positively charged mush with those little negative bits sprinkled in.
Like a blueberry muffin, maybe? But instead of blueberries, it's tiny electrons.
Okay, I can picture that. So that was our first attempt at drawing a picture of the atom. But of course, science is all about testing and refining, right? And the next big clue came from looking at light, specifically the light given off by heated gases. There's a crucial difference between the light from solids and liquids compared to the light from thin gases. What was it that really stood out?
Yeah, you see, when you heat up a solid or a liquid or even a really dense gas, you get this beautiful rainbow of colors, what I call a continuous spectrum. All the colors are there, blending smoothly into each other. But with those thin, rarefied gases, it's different. You get these distinct, bright lines of color at specific wavelengths, separated by dark gaps. It's like the atom is playing a tune on a piano, but it can only hit certain keys.
So instead of a full rainbow, it's more like a barcode made of light. And here's the truly fascinating bit. What was so unique about the spectrum of each element? Every single element had its own unique pattern of those spectral lines. Hydrogen always had the same set of lines, helium had its own set, and so on. It was like a fingerprint, a unique identifier for each element written in light. This told scientists that the way an atom was structured somehow determined the specific colors of light it could emit.
A light fingerprint. That's a fantastic way to put it. So scientists were like, okay, there's definitely something going on inside the atom that's causing this, but what? Enter Ernest Rutherford, stage left. In 1906, he comes up with this brilliant experiment. The idea was to probe the atom with these tiny, positively charged particles called alpha particles. You know, those things that come from radioactive materials. What was the whole point of this scattering experiment?
Rutherford wanted to get a sense of the atom structure by firing those alpha particles at atoms and seeing how they bounced off or passed through. Imagine shooting tiny bullets at a target to see how it's put together.
Oh, and speaking of those bullets, who actually carried out this experiment?
It was Hans Geiger and Ernest Marsden. And fun fact, Marsden was actually a very young student at the time. It just goes to show that you don't have to be a seasoned pro to make a huge discovery.
Talk about a memorable lab project. So how did they actually set up this experiment?
They took a source of alpha particles and, using lead blocks, basically created this narrow beam, like a laser pointer of alpha particles. Then they aimed this beam at a super thin gold foil, just a few atoms thick. It was like setting up the world's tiniest shooting range.
So they've got their alpha particle gun and this incredibly delicate gold foil target. What did they expect to see based on Thomson's plum pudding model?
Well, if the positive charge was spread out evenly, like in the plum pudding, they figured most of the alpha particles would just zip right through with maybe a tiny deflection, like shooting BB pellets through a cloud of smoke. They might slow down a bit, but nothing too dramatic.
Sounds reasonable. But hold on to your hats. The results were about to rewrite the atomic playbook. What actually happened?
The results were, well, mind-blowing. Most of the alpha particles did indeed pass straight through, indicating, yep, the atom is mostly empty space. But a small percentage were deflected at significant angles, some even bouncing back almost directly. It was like shooting a bullet at a tissue and having it ricochet back at you.
What? Talk about a scientific curveball. So what did Rutherford conclude from this completely unexpected result?
He realized that to cause such large deflections, there had to be something incredibly small and dense within the atom, packed with positive charge and most of the atom's mass. He called this dense core the nucleus. Only something like that could repel those positively charged alpha particles so strongly.
And that, ladies and gentlemen, is how we got the Rutherford atomic model, also known as the nuclear model. No more mushy pudding. So how did he picture the atom now?
Think of it like our solar system, but on a much, much tinier scale. There's a tiny, positively charged nucleus at the center, and the negatively charged electrons are whizzing around it in orbits, like planets orbiting the sun. The atom was no longer a blob, it was a miniature solar system.
It's amazing how much empty space there is inside an atom, right? It makes you wonder what's going on in all that nothingness. You mentioned an example 12.1, that illustrates this. Can you remind us what it was?
Right. Imagine you scaled up an atom to the size of our solar system, so the nucleus is the size of the sun. The electrons would be orbiting way, way out, much farther than Pluto even. It really puts that empty space into perspective.
It's kind of a humbling thought, isn't it? We think of ourselves as solid beings, but really, we're mostly made of empty space.
But hold on, there were still some big mysteries swirling around this new model. What couldn't Rutherford's model explain?
It still couldn't explain why atoms emitted light at only specific wavelengths, those distinct spectral lines we talked about. According to classical physics, orbiting electrons should constantly be radiating energy, which means they should be emitting a continuous spectrum of light, a full rainbow. And yet, we see only those specific lines. It's like a radio that can only tune into certain stations, and nobody knew why. And there's another even bigger problem lurking in the shadows, right? Something about the stability of atoms themselves.
Oh yeah, that was a big one. Classical physics predicted that any charged particle that's accelerating, and an electron whirling around a nucleus is definitely accelerating, should constantly be losing energy as it emits radiation. This would cause the electron to spiral inward and eventually crash into the nucleus.
That's not good. So if classical physics was right, atoms should basically be self-destructing all the time. And we know that's not happening because, well, we're made of atoms and we're still here. You also pointed out example 12.4, which shows how far off classical predictions were.
Yeah, if you applied classical theory to a hydrogen atom, it predicted that the frequency of light emitted by the electron should be the same as its orbital frequency, which would be incredibly high. But that's not what we see in the hydrogen spectrum at all. The observed frequencies are much lower, and they only occur at those specific values.
So Rutherford's model gave us a picture of the atom structure, the nucleus, and the electrons. But it couldn't explain why atoms were stable or why they gave off those specific colors of light. Then in 1913, along came Niels Bohr, and he was like, hold my beer, I've got this. He'd been working with Rutherford, but he knew the model needed some serious tweaking. What did he do?
Bohr took a really bold step. He said, okay, maybe classical physics just doesn't apply at the atomic level. And he borrowed ideas from this brand new and quite strange theory, quantum theory. He proposed three postulates, or rules, that govern the behavior of electrons in atoms. These postulates were like a set of new traffic laws specifically for the atomic world.
Okay, let's break down those postulates one by one. What was his first revolutionary idea about electron orbits?
Bohr's first postulate stated that electrons could orbit the nucleus in certain stable orbits without radiating any energy, despite what classical physics said. He called these orbits stationary states, and each one had a very specific fixed energy level.
So in these special orbits, the electrons were basically ignoring the usual rules of physics. What determined which orbits were allowed?
That's where his second postulate comes in. It states that the angular momentum of an electron in one of these stable orbits is quantized, meaning it can only have specific, discrete values, and those values had to be an integer multiple of a very tiny number, Planck's constant, divided by 2 pi.
Planck's constant. It's like the tiny ruler of the quantum world. It pops up everywhere. So the electron can't just orbit willy-nilly. It has to be in one of these specific quantized orbits.
Yeah.
And what about his third postulate? How did he explain those specific colors of light that atoms emit?
His third postulate explains that when an electron jumps from a higher energy orbit to a lower energy orbit, it emits a photon of light, and the energy of that photon is precisely equal to the difference in energy between the two orbits.
So it's those quantum leaps between energy levels that give us those distinct spectral lines.
Yeah.
And the bigger the jump, the higher the energy, and therefore the different color of light. Brilliant. Now, to solidify all of this, Bohr actually crunched some numbers. He came up with an expression for the radius of those allowed orbits. What did that look like?
He found that the radius of the nth allowed orbit, denoted by Arn, is given by N2H2, Me2, where an n is the principal quantum number, which can only be a whole number, like 1, 2, 3, and so on. Because of that n in the equation, the radius itself is quantized, meaning only certain specific radii are allowed for the electron. It can't just orbit anywhere it wants.
Quantized radius, like stepping stones around the nucleus.
Yeah.
And what about the energy of the electron in each of those stationary states?
Bohr also derived an equation for that. The energy of the electron in the nth stationary state, n, is given by AE4, 8 EVC2H2N2. For hydrogen, it boils down to, I guess, 13.6 electron volts divided by n squared.
And that negative sign, what's the significance of that?
The negative sign indicates that the electron is bound to the nucleus. It's like it's stuck in a well, and you need to give it energy to climb out.
I get it. So when the electron is in the orbit closest to the nucleus, that's the lowest energy state, right? That's the atom's chill-out zone.
Exactly. That's called the ground state. And for hydrogen, it has an energy of medical 13.6 electron volts. And to completely remove the electron from the atom, you need to give it at least 13.6 electron volts of energy. That's its ionization energy, the amount of energy needed to set it free.
It's like paying the electron's bail bond. And how do atoms get into those higher energy states, those excited states?
They can get there by absorbing energy, maybe by bumping into other atoms or by absorbing a photon of light that has just the right amount of energy to boost it to a higher level.
So for example, what's the energy of the first excited state of hydrogen, where n equals 2?
If you plug in n equals 2 into that energy equation, you get medley 3.40 electron volts. So to jump from the ground state at a negative 13.6 electron volts to the first excited state, you need 10.2 electron volts of energy.
And that energy difference directly relates to the frequency and therefore the color of the light emitted when the electron falls back down. Bohr's model beautifully explained the line spectra. When an electron transitions from a higher energy level to a lower one, the emitted photon's energy, given by high, is exactly the energy difference between those levels.
Exactly. It all fit perfectly. And conversely, if an atom absorbs a photon with the exact energy difference between two levels, the electron can jump up to a higher level. That's the absorption spectrum, those dark lines where specific colors have been absorbed by the atom.
It's like the atom is playing a cosmic game of hopscotch, jumping up and down those energy levels. This is a huge deal. Bohr's model earned him a Nobel Prize in 1922. But even with all its success, there was still a nagging question. His second postulate, the quantized angular momentum, it seemed a bit arbitrary, like why those specific values?
Yeah, that was a bit of a head-scratcher. But in 1923, Broglie came along and offered a really fascinating explanation. He was the one who proposed that matter, even tiny particles like electrons, can behave like waves.
Wave-particle duality. It's like the electron can't decide if it wants to be a particle or a wave, so it's like, fine, I'll be both. But how did this explain Bohr's quantized orbits?
De Broglie said that for an electron to be in a stable orbit, its wave nature had to satisfy a certain condition. The electron wave had to form a standing wave, like those vibrations you see on a guitar string when you pluck it.
So the electron wave had to fit perfectly around the orbit, like a snake biting its own tail.
Exactly. And to fit perfectly, the circumference of the orbit had to be a whole multiple of the electron's wavelength. Mathematically, that's 2 par equals no, where us is the de Broglie wavelength.
And what's the de Broglie wavelength of a particle?
It's given by up equals hp, where h is our trusty Planck's constant, and p is the particle's momentum. Now, if we substitute the momentum of an electron moving at speed VAN, we get 2 parm equals NONBN. Rearrange that and you get MVAN equals NH2. And guess what that left side of the equation represents?
The angular momentum. So Bohr's seemingly random rule about quantized angular momentum arises naturally from the wave nature of the electron. The only orbits that are allowed are those where the electron wave forms a stable standing wave. It's like the universe is the giant symphony and the electrons are playing their specific notes. That's incredibly elegant.
It really is. But as elegant as Bohr's model was, it wasn't the final word. It had limitations. For one, it worked really well for hydrogen with its single electron, but it struggled to accurately predict the spectra of atoms with multiple electrons because those electrons interact with each other in complex ways.
Right, it's like trying to predict the movements of a flock of birds. It gets messy. And there are other things it couldn't explain, like the relative brightness of those spectral lines or some of the finer details in more complex atoms.
Exactly. It was a powerful model, but it was limited in its scope. It was like a map that showed the major landmarks but didn't quite capture all the smaller details of the terrain.
So why do we still learn about the Bohr model today if it has all these limitations?
It's still important because it was such a pivotal step forward. It explained a lot of the key features of the hydrogen spectrum with just 3 simple postulates. It beautifully blended classical and early quantum ideas, and it demonstrated how sometimes physicists have to make bold assumptions and set aside certain problems to make progress. It paved the way for the development of quantum mechanics, which is the foundation of modern physics.
It's like it was the Model T of atomic models. It got us moving in the right direction, even if it wasn't perfect. So we've journeyed through the fascinating history of the atom, from vague ideas to Thomson's pudding, Rutherford's nucleus, and finally Bohr's quantum leaps, all tied together by de Broglie's wave concept. We've seen how experiments and bold theories led to a deeper understanding of the building blocks of the universe.
And it's incredible to think about the implications. The surprising amount of empty space within an atom, the quantized nature of electron behavior, and the mind-bending concept of wave-particle duality. These discoveries revolutionized physics and led to the development of technologies that we use every day.
And think about those unique spectral lines, the fingerprints of each element written in light. We use those fingerprints for all sorts of things, from analyzing the composition of stars to creating lasers and LEDs. It's truly remarkable what we've learned from these tiny invisible particles.
It really is. And Bohr's story is a testament to the power of creative thinking in science. Sometimes you have to question long-held beliefs and try something radically new. It's a reminder that our understanding of the universe is always evolving as we continue to explore.
So, dear listener, what new questions are bubbling up in your mind after this deep dive? Maybe you're curious about how quantum mechanics works in more detail, or maybe you're wondering about the even weirder things happening at the subatomic level. This is just the beginning of the story. We hope this has been an exciting and insightful journey into the heart of the atom. Thanks for joining us. Welcome back to the Deep Dive, everybody. Today we're going to be going deep on Chapter 13, Nuclei.
Oh, nuclei.
Yeah, sounds kind of textbooky maybe, but I think it's going to be pretty interesting.
Yeah, for sure. This is the fundamental building blocks of matter, right?
Right.
I mean, if you think about it, the nucleus is to the atom what a pinhead is to a classroom. It's that small.
Yeah. It's hard to imagine, right, how something so small could be so important. But the nucleus is like the tiny engine that powers the universe.
Yeah. That's what gives the elements their properties. It's what makes gold shiny.
Right. And it's what makes the sun burn.
Exactly.
So today we're going to take a deep dive into the nucleus and try to understand what it's all about.
Yeah. And we're going to do it in a way that's, approachable and fun. Even if you've never taken a physics class before, you should be able to follow along.
Right. We're going to be relying on some pretty cool material here.
Yeah, we've got some excerpts from a physics textbook.
Yeah. But don't worry, we're not going to just read it to you verbatim. We're going to break it down, make it fun, and most importantly, make it understandable.
Yeah, exactly.
So what are some of the big questions that we're going to try to answer today? Well, first of all, does the nucleus even have any structure?
Right.
Or is it just like a solid little ball?
Right. Or is it just a big mush?
Yeah. Yeah. And if it does have structure, what is it made of?
Right. What are the pieces? How do they fit together?
And how are those pieces held together? I mean, we're talking about protons and neutrons,
Right.
right?
Right.
They're both positively charged.
Well, the protons are.
Protons are positively
They're
charged.
originally neutral.
The neutrons are neutral.
Yeah.
But still.
They should be repelling each other.
Yeah.
So what's keeping them together?
Yeah, it's a good question. It's a really good question.
And then we also want to look at, like, the properties of nuclei.
Right.
Like their size.
Yeah. Their size, their mass.
Their stability.
How stable they are, you know?
Yeah.
Are they all the same? Are some of them more stable than others?
Yeah. And then, we want to talk about some of the cool stuff that happens when nuclei, get together and, like, interact with each other.
Right. Like radioactivity, fission, and fusion.
Right.
So,
yeah, this is going to be fun.
So to kick things off, let's talk about size.
Yeah.
How small are we actually talking when we say nucleus?
Like incredibly small.
Yeah. I mean, I know atoms are small.
Yeah.
But the nucleus is even smaller.
Oh, way smaller. Way smaller.
Like how much smaller?
So if you think of an atom as being the size of a football stadium, the nucleus would be like a marble in the center of the field.
A marble. So
Okay.
almost all of the atom is empty space.
Yeah, pretty much. It's mostly just empty space.
That's wild. Okay, so if it's that small, how do we even measure it?
Well, we don't use kilograms.
No.
Kilograms are way too big.
Right.
So scientists came up with a new unit called the atomic mass unit. It's abbreviated U.
2U.
Yeah. And 1U is about 1.66 times 10 to the minus 27 kilograms.
10 to the minus 27. That's 27 zeros after the decimal point.
Yeah, it's really, really tiny.
So this is the unit that we use to measure the mass of atoms and
Yep.
nuclei.
Yeah, exactly. It's much more convenient.
Okay. So when scientists started measuring the mass of different atoms using this new unit, they noticed something interesting, right? They found that the atomic masses were often close to whole number multiples of the mass of a hydrogen atom.
Right.
What did that suggest?
That suggested that atoms were built up of some kind of fundamental building block, some kind of basic unit.
Yeah.
But there were these exceptions, like
Right.
chlorine. Chlorine has an atomic mass of 35.46 U.
So not a whole number.
Not a whole number, so what's going on there?
Good question.
Well, it turns out that most elements actually exist as a mixture of different isotopes.
Isotopes.
Isotopes are atoms of the same element that have the same number of protons but a different number of neutrons.
Okay. So the number of protons determines what element it is.
Yeah, exactly.
Okay. So, for example, chlorine has two main isotopes.
Right.
Chlorine-35 and chlorine-37.
Right. Chlorine-35 has 17 protons and 18 neutrons. Chlorine-37 has 17 protons and 20 neutrons.
So they both have the same number of protons.
Right. That's what makes them both chlorine.
But they have a different number of neutrons, which gives them a different mass.
Right.
And the average atomic mass of chlorine, that 35.46 U, is just the weighted average of the masses of these two isotopes.
Yeah, exactly.
Okay. So even hydrogen, the simplest element, has isotopes.
It does. It has three main isotopes: protium, deuterium, and tritium.
Oh.
Protium is the most common. It has one proton and no neutrons. Deuterium has one proton and one neutron, and tritium has one proton and two neutrons.
And tritium is radioactive, right?
It is. It's unstable.
Okay. So back to the nucleus.
Right.
We said it's made up of protons and neutrons. Now, the proton is a positively charged particle.
Yeah.
And for a long time, scientists thought that the nucleus might also contain electrons to kind of balance out the positive charge of the protons.
Right. But it turns out that that's not the case.
No.
The nucleus doesn't contain any electrons.
And why is that?
Well, for one thing, it would violate the rules of quantum mechanics.
Okay.
Electrons are just too big to fit inside the nucleus.
Okay. So if there are no electrons in the nucleus, then what's keeping the protons from repelling each other and flying apart?
Well, that's where the neutron comes in.
The neutron.
Yeah. The neutron was discovered in 1932 by James Chadwick.
Okay.
He was doing some experiments bombarding beryllium with alpha particles.
Alpha particles. Those are just helium nuclei, right?
Yeah, exactly.
Okay.
And he noticed that this bombardment produced a new type of radiation that was neutral. It had no charge.
Okay.
And he realized that this radiation must be made up of particles that were about the same mass as protons but had no charge.
Neutral.
Yeah. And he called these particles neutrons.
Neutrons. Okay. So we've got our protons and our neutrons.
Yeah.
Now let's talk about some terminology. We've got the atomic number, the neutron number, and the mass number.
Okay.
What are those?
So the atomic number is the number of protons in the nucleus. It's represented by the letter Z.
Okay.
And it's what determines what element an atom is.
Right, so all carbon atoms have 6 protons.
Exactly.
Okay.
The neutron number is the number of neutrons in the nucleus.
Okay.
It's represented by the letter N.
Okay.
And the mass number is the total number of protons and neutrons in the nucleus.
Okay.
It's represented by the letter A.
A. Okay, so A equals Z plus N.
Exactly.
Okay. And we can use this notation to represent different nucleides, right?
Yeah, exactly. So, for example, the nuclide for carbon-12 would be written as 12 subscript 6 C.
Okay, so the 12 is the mass number,
Yeah.
the 6 is the atomic number,
Right.
and the C is the symbol for carbon.
Exactly.
Okay, got it. Now, let's talk about the size of the nucleus again. We know it's incredibly small, but how do we actually measure it?
Well, one way to measure the size of the nucleus is to use scattering experiments.
Scattering experiments.
Yeah, like the famous Rutherford gold foil experiment.
Right,
Where they fired alpha particles at a thin sheet of gold foil,
right,
and they measured how the alpha particles were scattered.
right.
And based on the scattering pattern, they could deduce the size of the nucleus.
So what did they find?
They found that the nucleus was incredibly small,
Like how small?
like on the order of 10 to the minus 15 meters.
10 to the minus 15 meters. That's a femtometer, right?
Yeah, a femtometer.
Okay.
Yeah.
So, like we said before, if the atom were the size of a football stadium, the nucleus would be like a marble in the center of the field.
Yeah, it's incredibly small.
But even though it's so small, the nucleus contains almost all of the mass of the atom.
Yeah, like 99.9% of the mass of the atom is concentrated in the nucleus.
So that means the nucleus is incredibly dense.
Oh, yeah. Incredibly dense, like way denser than anything we experience in our everyday lives.
Like how dense?
Like 10 to the 17 kilograms per cubic meter.
10 to the 17 kilograms per cubic meter. That's like squeezing the mass of a mountain into a sugar cube.
Pretty much, yeah. It's mind-boggling.
And the only reason the nucleus doesn't collapse in on itself is because of this strong nuclear force.
Right. The strong nuclear force is one of the 4 fundamental forces of nature.
Okay.
And it's the force that holds the nucleus together.
Okay. So how does it work?
Well, it's a bit complicated.
Right.
But basically, the strong nuclear force acts between nucleons.
Nucleons. That's just the fancy word for protons and neutrons, right?
Right.
Okay.
And it's a very short-range force.
Right.
It only acts over distances of about a femtometer,
Okay.
but it's incredibly strong.
Okay.
It's much stronger than the electromagnetic force, which is the force that governs the interactions between charged particles.
So it's stronger than the force that holds atoms together.
Yeah, much stronger.
Wow. Okay. So the strong nuclear force is what's keeping the protons and neutrons in the nucleus from flying apart.
Yeah, exactly.
But it's not just holding them together, it's also binding them together, right?
Right.
So there's energy associated with this binding.
Yeah,
And this energy is called the binding energy.
exactly.
Okay. So the binding energy is the energy that would be required to completely separate the nucleus into its individual protons and neutrons.
Right.
Okay.
Yeah.
And the binding energy is a measure of the stability of the nucleus.
Yeah, exactly. The more binding energy a nucleus has, the more stable it is.
Okay. So if we look at the binding energy per nucleon, we see that it peaks around iron.
Right.
And this means that iron is the most stable element.
Yeah, exactly.
Okay. And this is why iron is so abundant in the universe.
Yeah, it's the end product of stellar nucleosynthesis.
Stellar nucleosynthesis.
Yeah.
That's the process by which stars create heavier elements from lighter elements.
Yeah, so stars start out by fusing hydrogen into helium.
Right.
And then they fuse helium into carbon.
Right.
And so on, all the way up to iron.
Okay. And when they get to iron, they can't go any further.
Right, because iron is the most stable element.
Okay. So stars basically cook up all the elements in the universe up to iron.
Yeah, pretty much.
And then when they die, they explode and scatter these elements throughout the galaxy.
Yeah,
And that's where all the elements that we're made of came from.
right. So we're all made of stardust.
We are all stardust.
Yeah.
That's beautiful.
Yeah.
Okay. So we've talked about the structure of the nucleus. We've talked about the forces that hold it together. And we've talked about the binding energy.
Right.
Now let's talk about radioactivity.
Okay.
Radioactivity is the spontaneous emission of radiation from the nucleus of an atom.
Mm-hmm.
And it happens because some nuclei are unstable.
Yeah, exactly. Some nuclei are just too big or have too many protons or neutrons.
Okay.
And they're trying to become more stable by getting rid of some of their excess energy or particles.
Okay. So what are the different types of radiation that can be emitted?
Well, there are three main types:
Uh,
alpha, beta, and gamma radiation.
Okay.
Alpha radiation consists of alpha particles.
Right. And those are just helium nuclei.
Yeah. 2 protons and 2 neutrons.
Okay.
Beta radiation consists of either electrons or positrons.
Positrons, what are those?
Positrons are the antiparticles of electrons.
Antiparticles. Okay.
They have the same mass as electrons, but they have a positive charge instead of a negative charge.
Good.
And gamma radiation consists of high-energy photons.
Photons, those are just particles of light.
Yeah, but gamma rays are much more energetic than visible light.
Okay. So alpha, beta, and gamma radiation.
Right.
And these are all emitted from the nucleus of an atom.
Yeah.
And they can be harmful to living things, right?
Yeah, they can be, because
Yeah.
they can damage cells and DNA.
Okay. So we need to be careful with radioactive materials.
Yeah, for sure.
Okay. So we've talked about radioactivity. Now let's talk about nuclear energy.
Okay.
Nuclear energy is the energy that is released when the nucleus of an atom is split or fused.
Right.
And there are two main types of nuclear energy:
Right.
fission and fusion. Fission is the process of splitting a heavy nucleus into two or more lighter nuclei.
Right.
And fusion is the process of fusing two or more lighter nuclei into a heavier nucleus.
Exactly.
Okay. And both of these processes release a tremendous amount of energy.
Yeah, way more energy than chemical reactions.
Right.
Like 1,000,000 times more energy.
Yeah, a million times more energy.
Yeah.
Wow. So let's talk about fission first. How does fission work?
Well, fission is usually initiated by bombarding a heavy nucleus with neutrons.
Okay.
And when a neutron strikes the nucleus, it can cause the nucleus to become unstable and split apart.
Okay.
And when the nucleus splits apart, it releases energy and more neutrons.
Oh.
And those neutrons can go on to strike other nuclei, causing them to split apart as well.
So it's a chain reaction.
Yeah, exactly. It's a chain reaction.
Okay. And this is what's happening in a nuclear reactor, right?
Yeah. In a nuclear reactor, the chain reaction is controlled,
All right.
so it doesn't get out of control. And the energy that's released is used to generate electricity.
Okay. And this is how we get nuclear power.
Yeah, exactly.
Okay. Now let's talk about fusion.
Okay.
Fusion is the process of fusing two or more lighter nuclei into a heavier nucleus.
Right.
And this process releases even more energy than fission.
It does. It's the most powerful energy source in the universe.
Wow.
Yeah.
Okay. So how does fusion work?
Well, in order to fuse two nuclei together, you need to overcome the electrostatic repulsion between them.
Right. Because they're both positively charged.
Exactly. So you need to get them really, really close together.
Okay.
And you need to do this at incredibly high temperatures,
Okay. Like how high?
like millions of degrees Celsius.
Millions of degrees Celsius. Wow. So how do we create those kinds of temperatures?
Well, one way is to use powerful lasers.
Okay.
Another way is to use magnetic confinement.
Magnetic confinement.
Yeah. You can use powerful magnetic fields to confine the plasma.
Plasma. What's plasma?
Plasma is a state of matter where the atoms have been stripped of their electrons.
Okay.
So it's basically a soup of charged particles.
Okay.
And you can confine the soup using magnetic fields.
Okay.
And if you can get the plasma hot enough and dense enough, then the nuclei will start to fuse together.
Okay. And that will release energy.
Yeah.
Okay. So this is what's happening in the sun right
Yeah, exactly. The sun is a giant fusion reactor.
now. Okay.
It's fusing hydrogen into helium.
And that's what's giving off all the energy that we receive here on Earth.
Yeah.
Amazing. So scientists are trying to replicate this process here on Earth.
Yeah, they're working on building fusion reactors.
Okay. And if they're successful, it would be a huge breakthrough.
It would be. It would provide us with a clean, safe, and nearly limitless source of energy.
That would be incredible. So that's a pretty good overview of nuclei, right?
Yeah, I think so.
We've covered a lot of ground. We've talked about the structure of the nucleus,
Right.
the forces that hold it together, the
Right.
binding energy,
Right.
radioactivity,
Right.
fission,
Right.
and fusion.
Right.
And we've even talked about how all of this stuff is related to the stars.
Yeah.
So I think that's a good place to stop for today.
Yeah, I think so too.
But before we go, I want to leave you with a final thought.
Okay.
We talked about how the density of nuclear matter is incredibly high,
Right.
like much higher than anything we experience in our everyday lives.
Yeah.
But it's also incredibly consistent.
Right.
The density of nuclear matter is pretty much the same for all nuclei, no matter what element they are.
Yeah, that's right.
So what does that tell us?
Well, it suggests that there's something fundamental about the way matter is organized at the nuclear level.
Right.
It suggests that there's some kind of underlying structure or principle that's governing the behavior of nucleons.
And we don't fully understand it yet.
Not yet, but we're working on it.
And that's what makes this stuff so exciting.
Yeah, it's a big mystery.
So there you have it, the nucleus. A tiny, mysterious, and incredibly powerful object.
Yeah.
And that's the deep dive for today. Thanks for listening.
See you next time. All right, welcome back for another deep dive. Today, we're going deep, really deep into the core of, well, everything electronic.
Everything electronic, huh? That's a bold claim.
I'm sticking with it because we are tackling Chapter 14, Semiconductor Electronics, Materials, Devices, and Simple Circuits.
Ah, yes. The unsung heroes of the digital age. Those tiny components that power our computers, our phones, our everything. We're going to explore the fascinating world of semiconductors.
And we are diving right into the physics textbook for this one.
Don't worry, we won't be throwing equations at you. We're after those aha moments.
Right. No lectures here, just a deep dive into what makes semiconductors tick and why they're so important in our lives.
So where do we start with this deep dive?
Well, let's set the stage first. Before the semiconductor revolution, we had these things called vacuum tubes.
Ah, vacuum tubes. Like giant glowing light bulbs that made early electronics work.
They were power-hungry beasts, huge, fragile, needed a ton of voltage to run.
Not exactly the picture of efficiency, were they? You'd be lucky if they lasted a few months without needing a replacement.
Imagine constantly swapping out parts in your TV. Then, in 1948, boom, the transistor is born.
A true game changer. This marked the beginning of the solid-state electronics era.
Right. Instead of electrons flying through a vacuum, we could now control them within solid materials. And this was all thanks to the ability to control current flow with a solid-state gate. No more need for that clunky heated filament in a vacuum.
And the impact. Wow. Devices became drastically smaller, more energy efficient, and way more reliable.
I mean, think about your smartphone. All that computing power in your pocket. With vacuum tubes, that would fill a room.
Maybe even a whole building. We've come a long way.
And even from those chunky CRT monitors to the sleek flat screens we have now, it's all thanks to solid-state tech. It's like technology went on a diet.
Huh. You're not wrong.
And you know what's funny? Even before the transistor, people were using naturally occurring crystals for simple electronics. Like literally a crystal and a wire to detect radio waves.
Amazing. It's all about understanding how those tiny electrons behave in solids.
Okay, so we've established that semiconductors are pretty darn important. Now let's get down to the brass tacks. How do we classify these materials?
We can classify them based on a very fundamental property, conductivity, or how easily electricity flows through them.
Right. Metals, semiconductors, and insulators.
Exactly. It all boils down to how much resistance a material puts up against the flow of those tiny electrons, a bit like water flowing through a pipe.
So metals are like super highways for electricity. They have very low resistivity, copper wires, for example.
Right. Resistivity is measured in ohm meters, and for metals it's super tiny, 10 to the power of -8, even less sometimes.
On the flip side, insulators are like roadblocks for electricity. Rubber, glass, those kinds of things.
The resistivity is massive. Imagine 10 to the power of 19 ohm meters. No wonder electricity has a tough time getting through.
And then we have the middle ground, semiconductors. Not quite a metal, not quite an insulator.
Their resistivity is somewhere in between. And that's where things get really interesting.
Absolutely, because we can actually control how conductive semiconductors are, unlike those stubborn metals and insulators.
Temperature can affect it, and even tiny impurities can have a huge impact. We'll get to that later.
Right. Speaking of different types, we've got elemental semiconductors, the pure ones like silicon and germanium.
And then there are the compound semiconductors, a mix of different elements. They could be inorganic, like cadmium sulfide or gallium arsenide.
And even organic semiconductors like anthracene or polypyrrole. It's a diverse bunch.
Indeed. And while organic semiconductors are super exciting for the future, for this deep dive, we'll stick with the inorganic gang, particularly silicon and germanium.
Right. The fundamentals are pretty similar across the board anyway.
Now, besides conductivity, there's another way to understand how these materials work. It's a bit more abstract, but it's key. Energy bands.
Yeah, energy bands, not exactly a catchy term, but super important. It all comes down to how those tiny electrons are arranged in a material.
Okay, think of an electron in an atom as being on a specific energy level, like it's orbiting the nucleus on a defined track.
Right. But when you pack tons of atoms together to form a solid, those individual energy levels start to blur and merge together.
They form these bands of allowed energy levels, sort of like widening those distinct orbits into broader highways where electrons can hang out.
Exactly. The band holding those outermost electrons, the ones involved in bonding, that's called the valence band.
And sitting right above the valence band is another energy band called the conduction band. It's usually empty.
Why is it called the conduction band?
Well, for electricity to flow, electrons need to be able to move freely, and that happens in the conduction band. Think of it like the express lane for electrons.
So in a metal where conductivity is high, the conduction band is either overlapping with the valence band or it's just partially full already. It's like an open door policy for electrons.
Exactly. Always free electrons ready to conduct. But with insulators, there's a big gap between the valence band and the conduction band. That's the energy gap, or EIG.
And in insulators, this gap is huge. Like electrons can't even dream of jumping across. They're stuck in the valence band. No wonder insulators don't conduct well.
But now, let's talk about semiconductors. They have an energy gap too, but it's much smaller than in insulators.
So at room temperature, some electrons in the valence band can actually gather enough energy just from the heat around them to jump across to the conduction band. They're like, woohoo, freedom.
Exactly. And this smaller energy gap is what gives semiconductors their unique controllable behavior. It's like a gate that we can adjust to control how many electrons can jump into the conduction band and conduct electricity.
Now, when an electron makes that leap to the conduction band, it leaves a little vacancy behind in the valence band. That vacancy is what we call a hole.
And here's the twist. That hole behaves like a positive charge carrier.
Wait, a positive charge, but a hole is just an absence of an electron, right?
That's right, but think of it like this. When an electron from a nearby bond fills that hole, it leaves behind a new hole in its original place.
So it's like that hole itself is moving. And since it represents a missing negative charge, we can think of it as a positive charge moving around.
Exactly. In semiconductors, we have conduction happening thanks to both electrons moving in the conduction band and holes moving in the valence band. A two-for-one deal.
Now, this whole energy band thing gets even more interesting when we look at silicon and germanium crystals specifically.
Right. Silicon and germanium, with their N atoms, end up with 8 N possible energy states for their outer electrons. And those states split into two bands, the valence band and the conduction band, separated by that all-important energy gap.
The bottom of the conduction band gets labeled EEC, and the top of the valence band is EV.
And that energy gap, EIG, between them, that's what dictates how the material behaves electrically. It's like a thermostat controlling how many electrons can jump to the conduction band.
You can almost visualize it, right? Like figure 14.2 in our textbook shows. No gap. You've got a metal. A huge gap. That's an insulator.
And a moderate, manageable gap. Boom, you've got yourself a semiconductor.
Perfect. Now let's talk about those pure, undoped semiconductors. We call them intrinsic semiconductors, like silicon and germanium in their pristine form.
Both silicon and germanium have this beautiful symmetrical structure, each atom surrounded by 4 neighbors in a diamond-like lattice.
And they form these strong covalent bonds with each other, sharing their 4 valence electrons. A nice, stable arrangement.
But as the temperature rises, things get a bit more lively. Those thermal vibrations can actually break some of those covalent bonds.
And when a bond breaks, an electron escapes, becoming a free electron, ready to roam around and conduct electricity.
And that missing electron, well, that's a hole ready to do its positive charge carrier thing.
So in a pure intrinsic semiconductor, every freed electron creates a hole. They come in pairs.
Exactly. The number of free electrons, Nat, is always equal to the number of holes, NH. That's what we call the intrinsic carrier concentration, Nat.
And the total current flowing through the material is the sum of the electron current and the hole current.
Right. But there's also this constant dance going on between generation and recombination.
Right. While some bonds break and create electron-hole pairs, other free electrons are finding holes to recombine with, essentially canceling each other out.
Like a never-ending game of musical chairs, with electrons and holes constantly swapping places. And the music is thermal energy.
A great analogy. Now, there's this interesting example in our textbook about carbon.
Oh, yes. Example 14.1. It explains why carbon, even though it has that same diamond-like structure, isn't a semiconductor, it's an insulator.
It all comes down to that energy gap again. Carbon's ionization energy, which is related to EG, is way higher than silicon or germanium.
So even at room temperature, those electrons in carbon just can't muster enough energy to jump to the conduction band? Stuck in the valence band, no party for them.
So intrinsic semiconductors do conduct a bit, but not very well at room temperature. And that's where doping comes in.
Ah, doping. This is where we get to tinker with the conductivity of semiconductors, intentionally adding impurities to boost their performance.
It's like adding a secret ingredient to our semiconductor recipe to enhance the flavor.
We call these impurities dopants, and we add them in incredibly small amounts, just a few atoms for every million semiconductor atoms.
But don't underestimate their power. These tiny additions can have a massive impact on conductivity.
And the trick is to choose dopant atoms that are similar in size to the silicon or germanium atoms. That way, they can seamlessly slip into the crystal lattice without causing too much disruption.
Right, like a chameleon blending into its surroundings. And we've got two main types of dopants for silicon and germanium.
Pentavalent dopants, which have 5 valence electrons like arsenic, antimony, and phosphorus.
And trivalent dopants with only 3 valence electrons like indium, boron, and aluminum.
These two types lead to two different flavors of extrinsic semiconductors, each with its own unique properties.
So let's start with N-type semiconductors created by doping with a pentavalent impurity. Imagine one of these pentavalent atoms taking the place of a silicon atom.
4 of its 5 valence electrons will happily form bonds with its silicon neighbors.
But that 5th electron, it's like the odd one out, just hanging around, loosely bound to the dopant atom.
Barely clinging on. It takes very little energy for that 5th electron to break free and become a conduction electron, ready to carry current. That's why we call pentavalent impurities donor impurities. They donate those extra electrons.
And the number of these free electrons depends mainly on how much we dope the material, not the temperature. Intrinsic generation still happens, but those donor electrons just outnumber them by a landslide.
So in an N-type semiconductor, electrons are the majority carriers, and holes are the minority carriers. It's like a massive electron party.
Right, and all those extra electrons also boost the recombination rate. Holes become even rarer, quickly finding an electron to recombine with. It's a tough life for a hole in an N-type world.
Now let's switch gears and explore P-type semiconductors. These are made by doping with a trivalent impurity.
So picture a trivalent atom cozying up in the silicon lattice. It can only form 3 bonds with its neighbors, leaving 1 bond incomplete.
That missing bond creates a vacancy, or a hole, right there in the lattice.
And as we know, holes love to move around. An electron from a nearby bond will jump in to fill that hole, leaving a new hole behind in its place.
It's like a chain reaction of hole movement. And since each hole represents a missing negative charge, it's like a positive charge hopping around, contributing to the current.
So in this case, the trivalent dopant atom actually becomes negatively charged when it accepts that 4th electron to complete the bond. That's why we call them acceptor impurities. They accept an electron, creating a hole.
And in a P-type semiconductor, holes are the majority carriers, and electrons are the minority carriers. It's the hole's turn to party now.
It's important to remember, though, that both N-type and P-type semiconductors are still electrically neutral overall.
Right. The charge of the majority carriers is perfectly balanced by the opposite charge of those ionized dopant atoms.
So it's a delicate balancing act, and by doping, we're actually indirectly reducing the concentration of those minority carriers.
Now, when we look at the energy bands in extrinsic semiconductors, things get even more nuanced. In N-type materials, those donor impurities introduce a new energy level just below the conduction band.
We label this the donor energy level, Ed. It's so close to the conduction band that electrons in this level can easily jump up to become free carriers.
And in P-type materials, those acceptor impurities create an acceptor energy level, EO, just above the valence band.
It's like adding a stepping stone for electrons to easily hop up, leaving behind those mobile holes in the valence band.
And there's a beautiful relationship at play here. At thermal equilibrium, the product of the electron concentration and the hole concentration is always constant, equal to the square of the intrinsic carrier concentration.
We can see this in example 14.2 in our textbook. Doping silicon with just a smidgen of phosphorus significantly increases the electron concentration while dramatically reducing the hole concentration. It's like a seesaw. One goes up, the other goes down.
Doping really is an ingenious way to fine-tune the electrical properties of semiconductors. Now, are you ready for the next level of complexity?
Bring it on.
All right, then, let's talk about the PN junction. This is where the real magic happens.
The building block of diodes, transistors, and countless electronic devices.
So how do we create this mystical PN junction?
We take a P-type semiconductor, and bring it into very close contact with an N-type semiconductor. Often, this is done on a single wafer of silicon.
And at that interface where they meet, all sorts of interesting things start to happen.
First, we have diffusion. Remember those concentration gradients we talked about?
Right. High concentration of electrons on the N side, high concentration of holes on the P side. Nature loves balance, so those electrons want to spread out into the P region, and the holes want to spread out into the N region.
It's like they're trying to even things out. This movement of charge carriers creates a diffusion current.
But this diffusion party can't go on forever. As electrons leave the N side, they leave behind positively charged, immobile donor ions.
And as holes leave the P side, they leave behind negatively charged, immobile acceptor ions. It's like they're leaving their baggage behind.
And this buildup of charges right around the junction creates a region that's depleted of those mobile charge carriers, the depletion region.
It's like a no man's land for free electrons and holes.
And because of those separated charges, an electric field develops across this depletion region, pointing from the positive N side towards the negative P side.
And what does an electric field do? It exerts force. So this field starts pushing any stray electrons in the P region back to the N region.
And any stray holes in the N region back to the P region. It's like a bouncer at the club, keeping things in order.
This movement of charge carriers due to the electric field is called drift, and it creates a drift current.
And that drift current actually flows in the opposite direction to the diffusion current.
It's a tug of war.
Exactly. Eventually, a balance is struck. The electric field in the depletion region becomes strong enough that the drift current exactly cancels out the diffusion current.
So we reach a state of equilibrium. No more net flow of charge across the junction. We've created a stable PN junction.
Now, because the N material has effectively lost some electrons, and the P material has effectively lost some holes, a small potential difference develops across the junction.
We call this the barrier potential, or built-in potential, VUR. The N side becomes slightly more positive compared to the P side. It's like a tiny hill that those majority carriers have to climb to cross the junction.
Example 14.3 in our textbook highlights a very important point. You can't just physically stick a piece of P-type material to a piece of N-type material and expect a functional PN junction.
Right, you need that atomic level precision. Even seemingly smooth surfaces are rough at the nanoscale.
Exactly. Without that intimate contact, you won't get the proper formation of that depletion region and the built-in potential. It'll just be a bad connection.
So we've created our PN junction. Now let's turn it into a real device. The semiconductor diode?
Ah, the diode. Essentially a PN junction with metallic contacts added so we can connect it to external circuits.
It's like adding handles to our junction. And in circuit diagrams, we represent it with an arrow pointing towards a line.
That arrow actually shows the conventional direction of current flow when the diode is forward biased. And by applying an external voltage, we can change that equilibrium we talked about.
So let's talk about forward bias first. This is when we connect the P side of the diode to the positive terminal of a battery and the N side to the negative terminal.
It's like we're encouraging the current to flow in the direction of that arrow in the symbol.
And when we apply a forward bias, most of that voltage drops across the depletion region, opposing the built-in potential.
Right. The depletion region shrinks, and the height of that energy barrier gets reduced to V minus V, where V is the applied voltage. It's like we're lowering that hill for the majority carriers.
Now, if we apply a small forward bias, only a few really energetic majority carriers can overcome the barrier and cross the junction. So the current is small.
But as we increase the forward bias, the barrier gets lower and lower, making it easier for more and more majority carriers to cross over, leading to a rapid increase in current.
It's like opening the floodgates.
And something else really cool happens under forward bias. Minority carrier injection. Electrons from the N side, now finding it easier to cross, move into the P side, where they become minority carriers.
And holes from the P side cross into the N side, also becoming minority carriers there. It's like a cross-border migration of charge carriers.
And these newly injected minority carriers, concentrated near the junction, start to diffuse away from the junction into their respective regions.
This movement of minority carriers also contributes to the overall current flowing through the diode. It's a team effort.
Right. The total forward current is the sum of the hole diffusion current and the electron diffusion current. Typically, it's in the milliampere range, so a significant current.
Now let's flip the script and talk about reverse bias. Now we connect the N side to the positive terminal and the P side to the negative terminal.
We're now trying to push current against the preferred direction of the diode.
And when we apply reverse bias, that applied voltage still drops across the depletion region. But this time, it reinforces the built-in potential.
The depletion region widens. The barrier height increases to V0 plus V. It's like we're building that hill even higher, making it much harder for those majority carriers to cross.
So diffusion of majority carriers practically stops. But that electric field in the depletion region is still there, and it still acts on any minority carriers that happen to wander into it.
Those minority carriers get swept across the junction, creating a small reverse current. We call it the reverse saturation current.
And this reverse current stays relatively constant even as we increase the reverse voltage. It's limited by how many minority carriers are available, not so much by the applied voltage.
However, if we keep cranking up the reverse voltage, we eventually reach the breakdown voltage V.
And that's where things get a bit dangerous. The reverse current suddenly spikes, and if it's not limited, the diode can overheat and get damaged.
It's like pushing the diode too far, and it just can't handle the pressure. The same can happen under forward bias if the forward current goes beyond the diode's limits.
Right. It's important to respect those limits. So to really understand how a diode behaves, we look at its VI characteristics.
A graph showing how the current changes as we vary the voltage across the diode. It's like a personality profile for the diode.
In forward bias, we see a tiny current initially, almost nothing until we reach the threshold voltage or cut-in voltage.
Around 0.7 volts for silicon diodes, 0.2 volts for germanium. Once we cross that threshold, the current takes off.
It's like flipping a switch. In reverse bias, the current is super small, that reverse saturation current, and it stays pretty flat until we get close to the breakdown voltage.
Most diodes are designed to operate in those safe zones, far away from the breakdown point.
And we can also talk about the dynamic resistance of a diode.
This tells us how the diode's resistance changes with the applied voltage. It's calculated as delta V over delta I. Example 14.4 in our textbook shows how to do this.
It highlights how drastically different the resistance is in forward and reverse bias. Now, let's talk about a key application of the diode's one-way street nature, rectification.
Rectification. The process of converting AC, which flows back and forth, into DC, which flows in only one direction. Essential for powering most of our electronic devices.
The simplest rectifier circuit is the half-wave rectifier. We take an AC source, connect it in series with a diode, and then connect a load resistor across the output.
And the output voltage appears across that resistor only during the positive half cycles of the AC input.
Right, because that's when the diode is forward biased and allows current to flow. During the negative half cycles, the diode blocks the current.
So we essentially get a pulsating DC voltage using only half of the AC wave. It's a bit like chopping the AC wave in half.
And it's crucial to choose a diode with a breakdown voltage higher than the peak AC voltage. Otherwise, you risk damaging the diode.
A more efficient way to do this is with a full-wave rectifier. One common type uses 2 diodes and a special transformer with a center tap.
Each diode takes turns conducting during alternate half cycles of the AC input.
So when one end of the transformer's secondary winding is positive, one diode conducts. When the other end becomes positive, the other diode takes over.
The output across the load resistor now corresponds to both positive and negative half cycles of the AC input. More efficient conversion to DC.
Each diode only handles half of the total voltage, but together they make sure no part of the AC wave goes to waste.
There's also the bridge rectifier, which uses 4 diodes and doesn't need a center-tapped transformer. A bit more complex, but very common.
Now, the DC we get from these rectifiers is still a bit bumpy. It's pulsating, not that smooth DC we get from batteries.
Right. To smooth things out, we use filters. Often a capacitor connected in parallel with the load resistor.
That capacitor acts like a reservoir, storing energy when the voltage rises and releasing it when the voltage falls.
It helps to maintain a more constant voltage across the load resistor, reducing those ripples.
The time constant, which is the product of the capacitance and load resistance, determines how quickly the voltage falls.
A larger capacitance means a slower discharge and a smoother output. These capacitor input filters are widely used in power supplies to give us that nice, steady DC.
They're the unsung heroes that make our electronic devices happy.
All right, we've covered a lot of ground today. Let's recap.
Semiconductors are amazing, replacing those clunky vacuum tubes, giving us smaller, more efficient, and reliable electronics.
We learned how they're classified based on conductivity. with semiconductors occupying that sweet spot between metals and insulators.
We delved into the world of energy bands, with the energy gap being the crucial factor determining a material's electrical behavior.
Intrinsic semiconductors have equal numbers of electrons and holes, while doping lets us create N-type and P-type semiconductors with tailored conductivity.
The p-n junction is the heart of it all, creating that barrier potential and enabling diodes to act as one-way valves for current.
And rectification is the key process that uses diodes to convert AC into the DC that powers our world.
All thanks to the incredible properties of those tiny electrons dancing around in those carefully crafted semiconductor materials.
It's pretty mind-blowing to think that all this complexity arises from such fundamental physics. What future wonders await us as we continue to explore and manipulate these building blocks?
That's a question worth pondering.
Until our next deep dive, keep those electrons flowing.